Hi, Ted. Let us know when we want to start setting up for our presentation.
Hey, Donald, great. I've already uploaded your presentation as that was uploaded to the Plumbers website as of about 20 or 30 minutes ago. And so I'm ready to switch it over to you as soon as we're ready to start. We've got about 9 minutes to showtime. I'll be doing the sponsor slides and a quick administrative talk about how things go, and then we'll be kicking things off. So thanks for joining on, and I think we're all set.
Who's driving the slides? Is that you or me?
Once I actually give you presenter status, you will have arrows at the bottom of the presentation. Excellent. And be aware that wherever your mouse cursor is, there will be a little red dot. So if you want to actually use that to point out things on a diagram, that's perfect. If you don't want people distracted by a little red laser dot thing, then just make sure the mouse is outside of the slide window.
Perfect. I'm not sure if I was clear. Prair's going to be co-presenting with me. I don't think that's going to be a problem, but I want to give you a heads up.
No, presenter basically means you have access to the controls. There are like fancy things like screen share, and you can do set up a poll if you want to do a poll, but other than that, that's the only difference about being the presenter.
All right.
Zikis, for my slides, I want you to go through word by word with your little tracker. That's what I want you to do.
Not in a wavy fashion.
Oh, that's right. Just keep circling. That would be the best.
And while you're talking, I'm going to set up a poll: who likes dogs and who likes cats? Sing along, yes. I challenge Prair to sing his talk.
Okay, so far we have 23 people on. We got another 8 minutes to go, 6 minutes to go until showtime.
I'm going to turn off my camera for a little bit.
Ditto.
All right, we're at the top of the hour, so it's time to get started. First of all, just a couple of administrative notes. Per, could you mute yourself? You actually are causing a huge amount of echo. If you have earbuds or headsets, it might be good to use that so we don't get feedback from your mic and the sound. So it's sort of a good general presentation tip. Yeah, so first of all, just some administrative notes. I would like to thank all of our sponsors, since without them, this would not be possible at all. So quickly run through them. Facebook is our diamond sponsor. Platinum sponsor is IBM. Our gold sponsors are ARM and Microsoft. And our silver sponsors are AWS, Netflix, and Red Hat. The speaker gift sponsor is Collabra. The t-shirt sponsor is VMware. Please note that there will be a survey about how you found the the Linux Plumbers Conference virtual event that will be coming out at the end of the link will be in the closing keynote, and the first 200 people who respond will be getting t-shirts. So that's how the t-shirt handout is going to be handled. And of course, the Linux Foundation's provided conference services and a lot of administrative help for the Linux Plumbers Conference. I'd also like to very much thank the Linux Plumbers Conference Planning Committee. Everything that's being used for this conference is using open source software, from Big Blue Button to Matrix to Indico, which is running the conference website. And they've done a huge amount of work knitting all of the pieces together, LDAP for login, just so that everything would work. Those of you who were on Monday may have noticed that there was a Matrix chat server meltdown. Turns out that if you have a single-threaded Python server and 1,500 or so people trying to use it, things tend to melt down. And folks on the planning committee were like frantically making it be multi-threaded Monday night, which is how it worked on Tuesday. So a big round of thanks needs to go to the Plumbers organizing committee, without which this wouldn't have happened at all. A couple of other administrative notes. Just in case you didn't have enough Rust discussions on Monday, there is going to be an additional follow-on Rust session in Hack Room 4 at the end of the Plumbers Conference and Kernel Summit sessions today. There was email sent out by James with that and some other details. So I just wanted to call your attention to that. Just as a note, we do have both shared notes and the chat server. You may have noticed that it took a good 6 seconds to log into the chat server. If you would like to help take notes in the shared notes, my suggestion is to use either a Matrix client or the web client for the chat room, since switching between the shared notes and the chat tab is a little bit slow. The chat server is working, so we'll be doing questions on the chat. And if folks, if the presenters don't have a chance to answer your questions on the chat, feel free to respond to them on the chat after your session is done. Also, if you'd like to ask a live question, please turn on your video and then wait for the speaker to recognize you. Or if the speakers would like to take questions at the end, they can let us know, and then we'll do things that way. And with that, I'd like to introduce our speakers, Don Zikas and Purit. I'm probably going to butcher the last name, so I'm not going to even try. Sorry about that. I will be turning presenter status over to them and letting them go ahead and give themselves any kind of introduction or bio they would like. Let me find. Okay. All right, Don, you should have presenter status now.
I see it. Thanks, Ted.
Yeah. Is my audio better?
Yes.
Yes.
It was just the mic gain. Thank you, Ted.
All right. Thank you, everybody. Hello, welcome to our talk, Integrating GitLab into the Red Hat Kernel Workflow. My name is Don Zikas, and with me presenting is Prarit Bhargava. Today, we're going to talk about GitLab and how the Red Hat kernel team is using it for their workflow, and if there's an opportunity for the upstream community to increase its use of GitLab's services. So let's start with a simple question. How to get Linus to accept a pull request from GitLab? Maybe he already does, but my goal here is to help encourage more of that. So we know the community has looked at Git forges like GitHub and GitLab. There have been challenges. The services do not always conform to the kernel community rules. In some cases, they can be made to work. Regardless, I'd like to increase the usage of the services, at least for GitLab. Recently, the Red Hat kernel team went through a migration from a very old Patchwork v1 server to GitLab. The migration took about a year, and a lot of new tooling had to be incorporated. We worked with the GitLab development team to resolve a dozen or so issues. The relationship Red Hat has built recently with GitLab and the use of its services, we are looking to help lead the effort to improve GitLab overall to allow it to be a common alternative location as the source of pull requests for kernel maintainers. As I said, the Red Hat kernel team transitioned to GitLab this year. Before I have Prarit get into the solutions we implemented in GitLab, I wanted to talk about issues we had with our old workflow and how they're similar to some of the issues we see in upstream workflow. Like upstream, we had an email-based workflow with a central mailing list. Patches conform to the upstream posting rules with the addition of some extra metadata, that metadata being a Bugzilla tag and a build tag. Further, our reviews followed similar upstream rules, which meant we only accepted patches with an act by line, or we blocked patches with an act by line. And using Patchwork's patch processing, this workflow helped us organize and track what patches were posted and which patches were ready for inclusion. Over time, the volume of patches increased, and with the addition of CI, tracking the readiness of patches became very difficult for our maintainers. Our kernel maintainers turned to custom scripts to handle the tracking and monitoring of the volume. Of course, this was all tied to a Mutt-like client. We had strict internal review rules that allowed maintainers to only take patches when discussions were resolved and the correct developers act the patch. This led our maintainers to having to read almost every email to ensure those rules were met. Human typos frequently fail their automation rules, causing unrealized delays. We created sub-maintainers just like upstream, but that quickly turned into full-time jobs and not the promised part-time role. Next, even our reviewers struggled to figure out which patches they need to review versus what was already reviewed. Sorting unread and unreviewed email on a high-volume list is an art form. Reviewers frequently had to load a side web page that provided the summary status of the patches that needed reviews in order to keep up. Other quirks included having the CI process as a bolt-on and not fully integrated for easy access. It's hard to gate patches on a CI email box. Updated patch versions were tricky. RHEL posts large backports to update subsystems. Reposting a 100 patch set for a small change in a single patch generated noise for reviewers and maintainers. Getting those patches re-reviewed created more delays. And finally, our business logic wasn't front and center. The most frequent question around posted patches was, what is holding this patch set up? It wasn't obvious, and led to this side web status page I alluded to before. After about 10 years of this, our general process and exceptions around the process become complex. Our maintainers were reaching the limitations of handling the volume. We needed to make a change. This is where we turn to GitLab. Let me turn this over to Prayer to talk about how GitLab helped save our workflow.
Thanks, Don. As Don described, we had several significant problems with an email-based workflow at Red Hat. I'm going to go through how we fixed these problems and how moving to GitLab not only fixed issues for maintainers, but contributors and reviewers as well. Slide. I'm going to assume that most of you have seen or used the GitLab web UI. As part of my explanation of fixes, I'm also going to show you the output of a tool that Red Hat has heavily contributed to called Lab. Lab is a command line tool that interfaces with GitLab. And I want to show you the tool because I think most of us prefer working on the command line. And one of the fears of kernel maintainers, reviewers, and contributors is being forced to work on a web UI. Lab allows you to do anything the web UI does, including commenting on commits, opening merge requests, commenting on merge requests by opening up blocking threads, approving code and merging code, and many of the other mundane GitLab tasks. It's a powerful tool that is open source and supported by a small group of developers, and Red Hat is really involved in improving it. So let's look at the issues that Don brought up that were causing difficulty for the maintainers. The first of these was, slide, the customization of scripts. That doesn't seem like a big deal to most developers and reviewers, but as we all know, maintaining work scripts is an expensive endeavor. As Don said, each of our maintainers had different scripts to maintain a tree. This led to some cases where some maintainers would detect an error and another maintainer would not. GitLab provides webhooks, which are scripts that execute on a GitLab action. For example, a webhook can run whenever a merge request is opened. A webhook can run whenever a merge request is updated or commented upon. A webhook can run, really, on almost any GitLab action. We use the webhooks to remove much of the customization that maintainers were doing. For example, we have a webhook that verifies that there's a signed off by tag. Another example, and unlike upstream, at Red Hat, each change must be associated with a Bugzilla. So we have a webhook that verifies that a Bugzilla tag has been added to each commit and the merge request description. I'll get back to the merge request description in a few moments. Slide. Failures of the webhooks result in unique labels being added to the merge request. Continuing the Bugzilla example, if a commit was missing a Bugzilla tag, a Bugzilla needs review label would be added to the merge request, indicating to the contributor, reviewers, and the maintainers that something was wrong with the commit. The webhooks also add a public comment indicating that there was a problem with the commit and provides a pointer to our documentation, commit rules. We also have labels for missing signed off bys, incorrectly formatted commit messages, etc. But back over to that script customization problem. As I was saying, using the webhooks allowed us to minimize the amount of customization that the maintainers were doing. Part of that, as I just explained, was checking each merge request description and change set had a Bugzilla and signed off tag. We have the signed off by tag requirement because the merge request description is used in the merge commit. So we need a signed off by tag on that merge commit from the author. That is now all automated away in webhooks. And we've done a large amount of work to automate away as many of these simple tasks as possible. Slide. The next problem Don mentioned was that it wasn't very easy to track reviews. The great thing about email is that it's easy to comment on commits, descriptions, test results, or really anything else. The problem with email, however, is it isn't that easy for a maintainer to sift through all that traffic and find those reviews and comments. Maintainers at Red Hat, excuse me, and I'm sure upstream must read through each and every comment to determine if a commit is ready to be merged. GitLab solves this by automatically threading comments and replies. These, in GitLab parlance, are called threads, and all the threads are organized per merge request. Each thread represents one question about the code, and all of this is now easily tracked within the merge request itself. GitLab also provides an easy-to-use method to approve code. There's a big fat approve button on each merge request that signifies a reviewer's sign off that the code can be merged. Red Hat is migrating away from email-based reviews to using GitLab threads and approvals. And in fact, we no longer see anyone using email-based approvals. The approve button process was adopted quite quickly within Red Hat. The approvals are all tracked within the merge request, so maintainers don't have to sift through email to find them. Slide. Another problem is who has to do a review and who is responsible for a review. Upstream has long used the maintainers and get maintainer PL scripts so that contributors would know who to CC for a review. But that's just another step that contributors have to remember or configure in their Git hooks every time they check out a tree. We took the approach that all contributors have to do that task over and over again. So we automated it. The way it works is that when a merge request is generated, the webhooks examine the code in the merge request and assign maintainers and reviewers based on the data in our owners.yaml file. That owners.yaml file is synonymous with maintainers. And in fact, we use our owners.yaml file to create our own maintainers file called rhmaintainers. We have two categories of reviews: required approvers and reviewers. Required approvers are just that, required. Required approvers must review the change set prior to being merged into RHEL. Reviewers, on the other hand, can review, but their acceptance of the changes in the merge request does not gate that merge request. We also recognize that we have some engineers who are only interested in changes. They don't want to be formally recognized as a reviewer, but do want a notification of change because it might affect their code. For example, we have some network driver maintainers that want to be notified on core networking changes. We have tooling which anybody can sign up for and be notified when a change to a file or directory occurs. We've also added per subsystem ACKs labels. These are generated by the webhooks and indicate whether reviews from a specific subsystem are needed. For example, the ACKs x86 needs review indicates that an x86 maintainer must review the code, and the ACKs PCI OK indicates that a PCI reviewer has already approved the code. Slide. As Don mentioned, in the email workflow, our CI testing was kind of bolted on. It was completely separate from patch generation, and there wasn't anything that required a pass for testing. Our engineers learned to ignore testing results and were often confused by the results. With GitLab, and really any GitForge for that matter, we were able to integrate CI directly into the process. Okay, I'm going to take a quick sidebar here. Let's face it, CI testing isn't that exciting to most maintainers, but it should be. And it should be on the other side of the equation too. It's good that contributors, like myself, know their code is being tested. It does nothing but add stability to the kernel, and that's obviously a good thing. The problem, though, with email CI is that it's just not well integrated at Red Hat or upstream. Consider Intel's testing upstream CI. I'm not aware that CI is being run when I submit a patch upstream. I only get an email, sometimes days later, depending on the test queue, that says my testing passed or failed. I have no status indication that says testing is occurring. I have no easy way to look at the tests or discussing them with the test writer. I had a lot of problems to tackle in this testing area, and I could easily fill this 45 minutes and probably the whole morning detailing the work that Michael Hoffman and Veronica Kabatova and her team accomplished in this area. Some highlights are simple things. How do we identify and report a failure? That's something we're constantly improving on, and we still don't have right. We received a lot of feedback from our engineering staff on the failures, and we continue to improve upon things. We've set up documentation that specifically addresses failures so that contributors don't have to read through the entire CI documentation. Each test now has an owner, so that person's name is also in the testing output. They're aware that they may need to help diagnose logs, et cetera, related to their testing. So they may know they may be called upon by engineers to help diagnose test failures. How do we identify and report test failures that have nothing to do with the change set, like an infrastructure failure? As you can imagine, that's been difficult to figure out. But we've made some progress here, and the test infrastructure failures are slowly being identified and called out in the test logs. Slide. Reviewing isn't really a maintainer issue per se, but it's definitely worth bringing up as something which clearly impacts the maintainers. And most maintainers are actually reviewers. In the email-based workflow, reviewers had to take an email, save it, apply it to their tree, and hope it applied. There was a lot of process in just simply getting the patch set. Tools like Patchwork made this easier, but even that wasn't foolproof. It required manual intervention for new versions and other manual steps to get patch sets out. The convenient thing about a Git forge is that reviewers now work directly out of a Git repository. The unit of change in email was a patch set, and in GitLab, it's now a merge request. Reviewers can check out the merge request in their local tree and just look at it. Reviewers don't have to muck around with saving patches, etc. Reviewers can just look directly at the code as it was submitted, comment on it, and have it all contained within the merge request. And if a reviewer is really stuck in the old way of doing things, they can simply run git format patch to get emails and use those patches in their review process. GitLab will tell anyone who looks at the merge request exactly what the status of the change set is. If the change set in the merge request has a conflict due to someone else's code being merged, GitLab will notify in the merge request and in the email that there was a problem. If it's blocked by a review, there's an indicator for that too. If you still want a newsreader style output of all the comments across a project, akin to a mailing list, you can get that too. GitLab has built-in RSS feeds that provide a variety of levels of information. If you really want to see all the output from all the merge requests, you can subscribe to a feed that provides that. Or if you only want to see merge requests as they come in, there's a feed for that too. Slide. This is our shameless plug slide. Here are some links to projects where you can see our process in action. Arc and CentOS Stream are fully integrated into this process. As I briefly mentioned, one of the restrictions we have in RHEL and CentOS Stream is that all modifications require a Bugzilla. This isn't the case in Arc, however, so it's a little bit easier to make changes and see how things work there. We have detailed documentation for CentOS Stream that explains how you can contribute to CentOS Stream and includes links to our commit rules. And I've also included a pointer here for our tooling for contributors. And lastly, here's another link to Lab. If you're already using GitLab, I strongly encourage you to try out Lab. Its interface is trivial to learn, and once you use it, you'll likely never go back to using the web UI. From issues opened against Lab, I know several other large development groups have adopted its use. With that, I'll hand things back over to Don. Don, you're muted. You're muted.
All right. Thank you, Brett. Thanks, Brett, for that. As we spend more time with using GitLab, we uncover various issues. Over the past year, we've built up a relationship with GitLab to ensure we have a direct path with the development team to resolve these issues. We've worked with them to resolve and deploy at least 15 issues over the last 6 months. Most of this work is around API and tooling. In addition, we have a dedicated developer who is working on issues the GitLab team does not have the bandwidth to resolve. This has led to 2 MRs over the last 2 months that have been deployed. The point here is that Red Hat has a strategic relationship with GitLab and is willing to exploit that to help address any gaps as blocking upstream from utilizing their service more. Which circles back to my original question. How to get Linus to accept a pull request from GitLab? Again, maybe he does, but my real goal is here is how to encourage more use of it or allow people to experiment with it. So we're already familiar with some of the issues already with this. For example, chain of trust. There's been people talking about the chain of trust, about how PRs need from Linus to Linus need to be signed, including ones from a forge. I'm not sure if that's something that's a personal email configuration, or if that's something to do with a forge. There's that topic. Merge request logs. I've seen talks about concerns about how the merge request logs look in a forge, and maybe they're not exactly formatted in a way that upstream can utilize them. And there's a common one, I know Constantine's talked about this a lot, a single point of failure. What happens if GitLab closes shop and changes its behavior or get bought by another company? So that's a good question. How can we limit this risk by continuously pulling necessary data out of GitLab while retaining its services for development? So some of the things we've come up with is there's some interesting pieces of data that are important inside GitLab, and obviously there's a tree itself. You can mirror that. That's pretty easy to do. But I know Monday, I think Constantine's presentation talked about how comments are the breadcrumbs of decision making, and we have prototypes inside Red Hat that can take every comment to a GitLab project and spit them out to a public inbox if necessary. That way, all that information can continue to be made public, regardless if the service goes down or disappears or changes its terms of agreement. So we're looking to see if there's other pieces of information that need to be continuously pulled out of GitLab in order to alleviate that problem. And in addition, is there any other feedback or thoughts that people have that is blocking a more wider acceptance of GitLab that we can do to encourage and resolve? Obviously, it's not everyone's cup of tea, but it is. We do like to. I would like to actively encourage its use, and I want to know what people's thoughts are about how. What are some of the hangups? So, other than that, thank you, and I'd like to turn it over to questions to see what type of feedback we got. It's a very active chat.
It is very active, and there's a couple of things that I might want to address there, Don. One thing I think I saw Greg KH mention it, that he's keeps pointing back over at Garrett. Greg, I think one of the things that I want to stress, Zikis less so than myself. I'll admit this. He's smiling because he knows what I'm about to say. I'm not 100% convinced GitLab is the way forward, and nor are we saying that. We're obviously advocating for GitLab because we put a lot of resources into it, but a Git Forge model here also applies to what we had to do, and I think that's important for us to acknowledge that. I think that there's fear just moving from an email-based workflow to a Git Forge-based workflow, and we're trying to clear up a lot of that FUD that's out there. The second thing, Don, that I saw that was interesting. Actually, I'm going to get right. I'm going to zip down to Dmitry Vyukov. I hope I didn't butcher that name too badly. He asked, let me find something about resources. This is exactly what he wrote. This is just great in all respects. Do you have any estimation of the human resources involved in making this happen?
In integrating all the pieces, I'm not sure I fully understand the question. Now, obviously, what Prayer talked about, Red Hat has a more elaborate and complex business model. So we have certain rules about making sure everyone reviews it, the right review people, because it's liability as a product and yada, yada, yada. So what we implement is probably a little bit more complicated than what the upstream needs to implement. But as for, okay, I see you're integrating deploy and adding hooks and stuff like that. There is some complexity there. Webhooks aren't free. You need to stage them somewhere and set up servers. And we're working with GitLab to see how we can make this easier. I think GitHub added some features, allow this to make it easier, where you can just a couple clicks and they'll send out the hooks for you. GitLab is a little bit more complicated, unfortunately. But if this stuff is useful and you want to, I can work with GitLab to see how we can simplify it so it becomes a couple clicks or a configuration item, and we can roll it out. I think webhooks are one of the biggest perks we've had in our workflow. and automation.
Lukasz Stelmash, I think. Again, I'm going to apologize to everybody for butchering your names. My apologies. Has asked, does GitLab support matrix communication?
I have no idea.
I don't know the answer to that either. Constantine.
Actually, Daniel popped in. I wasn't sure if he had a question.
Oh, I didn't see that. Sorry, Daniel, did I cut you off?
No, that's fine. Look, I just want to pop my Patchwork maintainer hat on for a moment and say, internally, you've obviously clearly outgrown Patchwork, and I'm glad to see that you've got a solution that works better for you. There is absolutely no universe in which Patchwork would handle the sorts of things that you're doing.
We tried. We tried.
I know, yes. Yes. We got a lot of good contributions from Red Hat to Patchwork, for which I'm very grateful. I want to suggest for people with less complicated workflows, Patchwork has got better in terms of CI support. The NetDev BPF list and the Linux PPC dev list are examples where CI tests are getting run on every patch as it gets submitted. So we're trying on a bunch of these things. It will never be what Red Hat needs, but I think we are trying to get closer to what Upstream needs.
Excellent. Good to hear. Greg, did you have some comments? Oh, we lost Greg.
Yeah, I'm here. Sorry, wrong button. Turn the camera off. This is cool in that you added all the Garrett functionality onto GitLab, which is great because you guys need that for your internal tree. Other development trees have been doing this for a very long time. What is your sense of, I'm curious as to what sense of scale, how many patches are you dealing with? What's your rate of change? How are you, how fast, and what's your quantity that you're working with?
So our scale is a traditional RHEL Y-Stream update is about 15 to 16,000 patches every 6 months, broken across different patch sets. I mean, our patch sets are huge. We're back. I'm not sure if everyone understands.
Adding 15,000 patches per every 3 months?
Yes.
Okay.
Again, I'm not sure everyone understands the RHEL development model. Is we fork a tree.
Yeah, I do. I'm just kind of curious as
back
to
for
how
hundreds
fast,
of patches. It's kind of silly.
Right. I'm just kind of curious as to how, because if you look at some of the development trees we got today, we're running at what, 9, 10 changes an hour is what's getting merged in Linus's tree, right? That's a rate of change.
Exactly. No, agreed. Small changes all populated from different maintainers tree. And again, we tried to emulate that model for a number of years using an email-based workflow. Our business logic just kept getting in the way.
Okay, so that's cool. So it's for a medium-sized project like yours, that works well.
Sure.
I'm just trying to get a sense of scale. I mean, you couldn't centralized system with 10 changes an hour isn't going to cut it. I know Kubernetes had to really beat on the back end to try and make a rate of change that fast to get GitHub and that CI workflow working well.
Yep.
So this is nice because that's more than like Android has, but it's way less than what the kernel has. Did you see Constantine's talk about before and why the kernel community can't do centralized infrastructure? I
saw his talk. I don't remember the arguments for why centralized. And again, don't get me wrong, I'm not looking to have GitLab be the place for development. I'm just looking, every sub-maintainer can have its own workflow. If some choose to do GitHub, Garrett, Patchwork, maybe GitLab can be part of that piece. I figure each sub-maintainer has its own style workflow. The end result is you collect all the patches in a GitLab instance and you do a pull request to Linus. Linus can do his own workflow. I'm not looking to centralize it, just trying to give it an opportunity.
Centralizing a subsystem, which is scary. I know DRM did this, right?
Yes.
But you are centralizing a subsystem, and that has the potential to cut out
the sub-maintainers choosing to centralize the subsystem.
Right, they do. I agree, but if you do that, like, so if it happens to be on GitHub, you just lost China, right? Because they can't contribute using that. there are issues involved there, right? And
which is why sub-maintainers got to make the right decision, right? I mean, I can't choose for them. I'm just trying to provide the opportunity.
oh, that's cool.
If time is an issue, we can work with GitLab.
No, that's cool. So, but my other is this all pushed back into the regular GitLab infrastructure, so it now emulates the Gerrit workflow, basically?
We looked at Gerrit. People had some struggles with using it effectively in their workflow, so we kind of leaned away.
You added all the features that GitLab was missing that Gerrit provides,
Probably
like owners and checking the signed off by and all that infrastructure tools that Gerrit provided. That's cool. That's fine, but it's just kind of funny to watch.
They reinvented the wheel.
Greg, if I may interject, sorry, Zach, I didn't mean to cut you off. Greg, if I may interject, I remember that we sat down at some point and looked at the Git forges, and this was 2.5 years ago, probably. I don't know how far Gerrit has leapt forward in that time, but I remember back then they didn't have a lot of these features then. So I think maybe things moving forward, they've maybe implemented some of this stuff. But I remember
the sense of scale when, but
yeah.
But also remember, Gerrit is self-hosted. It's not.
Oh, absolutely.
So
absolutely. Again, while we are using GitLab, we're not suggesting that it be the place. But certainly, if we, one of the concerns one of the questions we're asking here, which is Zix's question on the first slide, is effectively, could we push code from GitLab and have Linus accept it?
Well, he takes a pull from any maintainer's tree, no matter where it is. That's not an issue.
Okay. Well, he had some comments the other day.
Well, he does. I mean, he wants to make sure it's a signed tag, and we trust the infrastructure. But
sure.
If you look, he pulls the DRM tree, which I think is hosted on a GitLab instance today.
I thought it was set up on a clone somewhere, but okay, maybe. I know DRM is.
I know, but I'm saying that's the only rule: sign tag, trusted maintainer, tree somewhere, right? The workflow is what is the more important thing, not the location.
Right.
So what subsystem maintainers are you going to work with to convince them about this?
Whoever wants to.
Don't you have some on staff that work with this flow today that love it so much they want to do it for their open source work?
I mean, I work with the DRM team a lot.
So they have their own already. I agree, but I'm just saying. Your existing maintainers that work for you that are used to this are willing to do it.
Yeah, I mean, speaking as an existing maintainer, right, one of the things that I've always been really worried about is we have to collaborate with other subsystems. And that means that if there is information that ends up getting orphaned such that it's only available on a website, I'm going to get worried about that. Now, if it's stuff like, say, integration testing is currently being done separately anyway, right? I mean, whether we do it on Kernel CI or it's integrated into a GitLab CI flow, it's a separate website. And to be honest, if you think about the noise that might get involved if we try to inject a huge amount of, CI, reports through email, I could imagine that getting, a little bit daunting. But the thing that I really, really worry about is discussions, right? I think one of the big worries people had with Gerrit is if you have comments for the code review that are on Gerrit, they're not available anywhere else. And it's made worse by the fact that Gerrit can be self-hosted. Although, again, I'll note GitLab can be self-hosted, right? I mean, we could run a gitlab.kernel.org, right? But suppose we did that, right? Now we might have some portion of the comments on gitlab.kernel.org and some portion of the comments that are on the mailing list, right? And so I imagine you may have had that situation when you were transitioning from an email-based workflow to a web-based workflow, where at a certain point it started, shifting, because if you needed to do a search, now you had to search the mailing list
You built an
and
email bridge.
the
You
Git
built an email
forwards,
bridge
right?
that worked
Yeah.
both ways. Yep.
Yeah, so either that or you have to basically do something where in theory one could set it up so that all of the GitLab discussions end up getting mirrored onto the mailing list, right? And I don't know how well that would work, right? But that would be one of my concerns, right? So suppose ext4 used a GitLab instance, right? Well, I don't really care which one it is, right? And I'm having a conversation that also needs to include the XFS folks, right? Or the MM folks, right? Now, if we look at what Bugzilla did, they were trying to include all of the web metadata in the email. So even though we had email Bugzilla integration, the email looked really ugly, right? And it's sort of a question of, is it initially a web-based system first, or is it a mail-based system first, right? So if you look at LKML plus lore, it is email first, and then we've added the web backend as an adjunct so that we can do better searching and all the rest. But it's clear that email was the primary. And so the challenge I see if I were a subsystem wanting to actually try to use this is if I have to work with some other subsystem that is still in the email first paradigm, and we need to have a joint conversation with them, right? That was the problem we had with bugzilla.kernel.org, right? Which was you knew it was coming from bugzilla.kernel.org, and people said that it looked ugly and it broke email chaining and a whole bunch of other things. And so to me, that's sort of the challenge, which is if we wanted to make it work, right, that would be my first question is how do I make sure that I can, that email continues to remain a first-class citizen, right? Maybe GitLab also becomes a first-class citizen, but they have to be co-equal, or I can't imagine how we would make the transition work.
Okay, that's fantastic feedback. So we do have an email bridge right now. That's how we transition people who are used to email into the new tools, and we set that up for a year. And it's actually running on the Fedora Rawhide space currently as an example. We didn't plan on propping up for a long time. We're hoping that we can transition to the tools, but you bring up a fantastic point. It's one of the biggest internal pain points, probably from the file system team at Red Hat about discussions, about how do you continue discussions on going from GitLab to a team that's used to email collaboration and easily CCing people. So we're still working through this pain point. GitLab isn't perfect yet, but again, we're trying to collect feedback to figure out how we can, over time, transition it to something that's a lot more usable and solves the problems exactly like you just said. And I'd love to tackle that problem somehow. Thank you, Ted.
Constantine, please go ahead. You've been waiting so patiently.
I just have a general comment that the main reasons why I'm not really excited about putting GitLab or any other solution like that at the kernel.org is that we have an experience of Bugzilla, which Ted already mentioned, that it's a tool that is sort of have been used, it's been largely abandoned, but we are now stuck with basically trying to remove all the spam. Like a chunk of my day is just removing spam from Bugzilla. And there's tools I can use I've used tools to simplify this, but my concern is that once the tool is added, it is almost impossible to then remove it because there's a couple of people that will be dependent on it, and a couple of workflows will be dependent on it. So adding a central feature at kernel.org like this just guarantees that we are going to have to maintain it for the next X years, regardless of how few people use it. Now, the problem is that if it's knocked out, right, I mean, kernel.org is not hard to DDoS. We don't run huge infra because primarily it doesn't matter that we are out or not. If you can't reach kernel.org, development does not stop, right? If somebody DDoSes V'ger, if V'ger is down for some reason, people still exchange emails and send badges around and work still gets done. It's an inconvenience, but it's not everything stopped working so we can't get anything done kind of situation. So if we add a central feature like this, and it goes down because either I screwed up and something's unavailable, or somebody's maliciously actively trying to make it not work. My concern is that how do we avoid the situation where nothing can get done because somebody doesn't want to get done. The usual example I have is that there's a 0 day that affects billions of devices worldwide, and you are an attacker who wants to make sure that it doesn't get patched for as long as possible, right? So you will attack any infrastructure that is aimed at fixing this problem. How do we avoid the situation? If they have to go back to email, then we haven't really solved anything, right? We're still falling back to email. So the email is still the primary mechanism of making sure stuff is done.
Right, and that's why we chose GitLab.com as our hosting site, because they're replicated across geos and they use Google Cloud underneath. To kind of it doesn't eliminate the risk, but it mitigates it, because they have that's a little bit more infrastructure than kernel.org is. I don't. Other than that, I don't think I have a clear answer to your question.
But if you're using Google Cloud, then suddenly you have chunks of the world that cannot use it, right? That is another problem, right? There is China that has trouble accessing Google services. A couple of weeks ago, Russia had trouble accessing some Google services because every now and again, politics gets involved, and suddenly a large cloud provider becomes a not acceptable solution. So then people say, well, host it on your own. Then you have a problem of, well, how much do we have to pay, and how far do we want to scale this to be able to make it accessible for everybody?
Fair enough. And we have a large test team in China, so that would impact the Red Hat's ability to deliver its raw products if that was the case. So we know GitLab works in China because of that. But you're right; these are good questions. I don't have clear answers to, and I guess that's why you advocate for email, because email is so redundant.
Well, I advocate for a distributed. Email currently is the only sort of solution that we have. I'm not saying we should stick to email as long as possible, only because currently we're using it. It works. It's distributed. You don't have to rely on any one company. There's a lot of good stuff that is actually built into email that we kind of don't really forget, but we suffer from bad corporate decisions that are around email, right? Trying to attempt to solve this by removing SMTP gateways out of the way. But I'm not opposed to subsystems doing this on their own, or doing it within companies, or asking us to do it, as long as it doesn't become an opaque place where discussions go and die there, right? We want to be able to see them. We want to be continuously export them out. Like I said, let's provide a public inbox of all activity that's happening, so that we can monitor it and people can query it, and people can see what is actually happening at a GitLab instance here or a Garrett instance there. And two, let's make sure that if something happens and the infrastructure goes away, or somebody pulls a plug and says, we're done, this didn't work out, that this doesn't just die in some database that gets dumped and never really referred to. We want to make sure that there is a fossil record that exists, people can go back to and can refer to, which is part of the reason why lore is such a good thing, because there's email that's there from the 90s, from 2000s, that we can go back, we can dig and figure out what happened. How did all this come into place? What is the decision trail?
But dumping GitLab data to public inbox solves a chunk of this, but not all of it, right?
As long as you can retrace decisions, I think that's all people really want to know. And like, if you can dump the patches and reviews that are in a format that is cross-platform as much as you can, which is usually Git format, patch format.
Right. And that's what we have some prototypes in house to kind of do that, using public inbox as an output. But I think we talked about this before a couple of days ago, is that it is a one-way street. And I think you were looking for a two-way street in some situation.
I'm not, but other people would really want it to be two-way street, because they don't want to have to go to like this subsystem site to suggest a feature, this subsystem site. People who work across trees, right? They usually the security people, they want to say, let's fix this bug situation so it doesn't happen anywhere. So they need to work with every subsystem. Currently, it's just a bunch of CCs and a bunch of mailing lists, right? But if they have to go to this GitLab here and this GitLab there and that Garrett there and this thing there, just to coordinate everything, I think that's going to degrade the process instead of really improving it. And yes, it improves in parts of it, but then it will make it worse for others.
Okay. So what I'm hearing from all these conversations is that it's not the tool itself or the service itself that people are against, or not really, or not against isn't the right word, but it's really preserving the conversation. It's the collaboration that people aren't convinced that GitLab can handle correctly, that the kernel community has developed over the last 10, 20, 30 years. Is that an accurate statement?
Sort of, yeah. When you look at the, Linux has been around for 30 years. How do we make sure that 30 years later, we are not sort of a bunch of fiefdoms that nobody really knows what happens around? Right? How do we keep this as inclusive and as decentralized as possible as we've had it up to this point?
Do you see email being still usable 30 years from now?
Some sort of messaging platform, right? If it's not email, then it has to be something else. But it needs to remain decentralized. At least that's what I try to push for.
Still using IRC.
Sorry, Clark, what was that?
Yeah, we're still using IRC. We need to start looking at the idea of putting together an interchange format. I mean, we're talking about the same sort of artifacts here, right? We're talking about discussion of why we should do something, and then an implementation detail. It says, here's a patch. This fixes this problem we were talking about in this discussion. Maybe we could come up with some sort of JSON or XML format that says this is how you describe a discussion on a particular problem, and here are some artifacts that address it, and then we could do some translation stuff to pass that thing around, so that from out of GitLab could flow the discussions and gateway them into LKML to be stored in lore. Do the same thing in GitHub. Garrett, I don't know. Is it a problem? That seems to be the theme that's coming through in all the discussion here. Is not, oh, we hate GitLab or we hate Gitforges. It's not really that. It's the fact that information flow is the important part here. Redundancy and distributed, resilience in the face of attack or failure. So, and right now, yeah, email is kind of the de facto standard. So
you hit the nail on the head there. That's the feedback that I think I'm getting from this. Is it's not necessarily the choice of the Gitforge, but the transfer of information. And Constantine said it's got to be a two-way street.
Yeah, there are folks that hate GitLab or GitHub with the heat of 1,000 suns. That's fine. That's the way it is in our world. But I think
most people are wrong. I'm just
yeah. But I think it's how do we take these various environments and make sure we don't lose the flow of ideas and patches. So that's the takeaway I get here.
Oh, we're really over time, aren't we?
Yeah,
Okay.
I was going to say we're I want to give people at least a couple of minutes of bio break before we start our next talk at the top of the hour. I think this is not the end of the conversation. Clearly, there's a lot more to be said here, and certainly, I think one really good thing that things like Gitforges like GitLab point out is what could be, right? I mean, the automatic integration of CI test with patches being proposed is a really good idea, right? And so whether we use GitLab to do that, or we get Constantine to maybe put in some kind of automatic bridge between B4 and kernel CI, clearly there is some good stuff in the workflows and other experiments you've done that, it's like Garrett has been improving, GitLab has been improving. If we want an email-based workflow to continue to be vital, we're going to have to step up our game, right? And so I think just simply showing us what you can do with GitLab is really, really useful. And I want to thank you for doing that in that presentation. Even if you haven't, convinced all of us that, we should just jump on the GitLab bandwagon tomorrow. So
what? I wasted 45 minutes and I didn't convince anybody? What?
Yeah. So thanks so much. I'm sure the conversation will continue, and let's give people a 5-minute break before we start the next talk.
Thanks,
you,
everybody, for all the
everybody.
feedback. I appreciate it.
Thanks. All right, we're at the top of the hour. People are still trickling back, so I guess we'll give folks another minute or so to come back on. Sanjay, are you ready to get started?
Do you hear me now?
Yes, we can hear you now.
Oh, good.
Great.
Yeah, I'm ready.
Okay, great. So you can turn on your video camera when you're ready, and we will be getting started in just a moment. Okay, I see a whole bunch of people who are active on the chat, but who haven't responded to the poll. So I'm going to assume that they're actually back and ready. So why don't we get started? And let me switch the presentation over to yours, and I will give you presenter status. So next up, we're going to be talking about Damos and how to use it to create a fine-grained access pattern kernel module as a quick tutorial. So Sanjay, why don't I turn it over to you?
Okay, thank you very much for the introduction, Ted. So let's start. So first disclaimer, the views expressed herein are those of the speaker. They do not reflect the views of the employer. And I have a cat, so my cat might come up on the screen, so please don't be scared. So let me introduce myself first. So my name is Songjae Park, and I am currently working as a kernel hypervisor engineer at Amazon Web Service. And I have interest in the memory management and the parallel programming, and currently developing Daemon. So in this talk, I will not explain how Daemon works internally. If you want that, you can refer to other resources in the project site or the source code. Rather than that, I want to explain how and what kernel hackers or their kernel subsystems can get from Daemon, and its not yet mainlined future features. And I'd like to also explain not about the things for user space, because this is the Kernel Summit. And I will also discuss about future plans on extending Daemon for more usages and improving Daemon itself and enhancing memory management subsystems with Daemon. So this is the overview of this talk. So first motivation. So we are showing that the demand for memory is increasing by showing the memory to CPU ratio on the AWS instance, but we don't see that the DRAM supply is following the track in physical machines. So we don't have enough supply. And that means that the memory management efficiency has been always important, but it's becoming even more important now. And Linux memory management subsystem works well, but it uses only not so fine data access information from my perspective. And that's mainly because of the monitoring overhead. And therefore, I have started developing Daemon. So the Daemon is a framework for general data access monitoring. It provides access frequency of each memory region, and it allows users to practically trade the monitoring accuracy for less overhead. So it's just a trade-off, just a practical trade-off, but it tries to provide best effort accuracy under the condition, and also it tries to minimize the overhead as much as it can under the given condition, which user has specified. And users can also set upper bound of the overhead regardless of the memory size of the system. So in short, conceptually, it scans all the monitoring target memory for every 5 milliseconds with less than 2% CPU utilization. I will show the evaluation in detail in later slide. So the source code is currently available in the development tree, of course, and there are several not yet mainlined features. And also we have backwards of the development tree on upstream 510Y and 54Y stable series. And also we have merged those in Amazon Linux kernel or version of the 510 and 5.4. And also the essential part of the daemon works has been mainlined from 5.15 RC1. And also we have a user space tool and a test suite that available on the GPL v2. So let me introduce how you can use daemon via the programming interface rather than the user space interface. The first step is to setting the request, the monitoring request in the daemon context struct. In the object, you should explain how and what memory regions for which other space you want to be monitored by daemon. And also you should register where monitoring event notifications should be delivered. In other words, some callbacks. So then the users can read the monitoring research or clean up things or doing some more funny works that they want to do with the monitoring research inside the callback functions. Then the second step is just starting daemon with the request that we have specified in the daemon context object by calling daemon start function. Then a kernel thread for the monitoring will be created and it will serve. Then you can do your work in the notification callbacks. In the notification callbacks, you can reach out to monitoring research by iterating through the daemon regions struct in the daemon context struct. After that, if you are done, then you can finish the monitoring by calling daemon start function. So let's do the live coding of a daemon-based kernel module. So we will write down a kernel module that doing the working set size estimation. It will receive the PID of a process as a parameter and then calculate working set size of the process using the daemon and monitoring research and then log it every 100 milliseconds. So from this point, let me share my screen. Yeah. So I have prepared the boilerplate. So the boilerplate code is just simple. It's just a hello world kernel module. Also, the make file also has no secret. So first, we will need to have a parameter to get the target ID. So, have a variable. Let it be put it as a parameter. And to use daemon, as I have explained before, we need the context object, and also we will need to get the PID and the PID later. And for this, because we need to use the daemon context, we need to include daemon.data header file. And also then now we will create the context in init and clean up in exit functions. So the first thing we need to do is allocating new context arrow. And we need to specify we want it to monitor the virtual address space of a process. Then we will find and get the PID or user specified PID. Check error. And we need to make a daemon target object, which will have the PID as its ID. And we put the target in the context. That is the notification callback. So this callback will be called for every aggregation interval, which is 100 milliseconds by default. And then we can start daemon and return the error code. And so we should also write the callback, but before that, let's write the kernel first. If the context is there, we stop the daemon. Clean up the context. This will also clean up all the objects that are registered in the context, including the target. And that's that because we have got the PID on our own. You should put that on our own. That's it. And we can now write down the callback, which we can do our real interactive works. The monitoring result is provided by the struct daemon region, as I have explained in the slide. But we should first iterate for all the targets in context because we can register multiple targets. So in this case, we are monitoring only one process, but we can monitor multiple processes. And here we iterate for all the regions in the target. If the region is accessed at least once, then we increase the WSS variable with the region's size and log the WSS. Quite simple, right? So here. Okay. Line 62. Oh. Okay, guilty. Now, the next thing so we have live coded the simple working set size estimation module within, I guess I have done that in 10 minutes. So actually it's very simple and only the 7 lines of code in essence for starting daemon was used. And now let's test the module. So for the testing, we will test that against an artificial access pattern generator program called MASIM. It will allocate 10 10 megabyte object and then access all objects for first 10 seconds, but then for only first one for 5 seconds and second one for 5 seconds and so on. So we can expect that the process will have 100 megabyte RSS while the module will report only 10 megabyte working size after the first 10 seconds. So from the artificial access pattern generator here, and we will use this access configuration, which has the 10 objects. So we expect the artificial. Before that, I'd like to also show you a script that I will use to monitor the RSS and the module reported working size. It's just a simple while loop graphing VM RSS from the status file of the process and graphing the message for the module's log. So let's start the access pattern in background. Just return module and pass the PID and show the RSS and the module reported working size. So as expected, the RSS is about 100 megabyte, but WSS that reported by the module is only about 10 megabyte. So I'll finish the demo. And let me go back to presentation. Yep. Yeah, so we have tested the module and we have also confirmed that it works as we expected. Now, evaluation. So how lightweight the daemon is. For our testing environment, which runs on i3.matter AWS instance and with 25 realistic benchmark workloads from Parsec3 and Spread2X, we have ran the virtual address monitoring and the physical address monitoring using daemon and measured the runtime and daemon's CPU usage. According to that, the daemon makes the workload 0.62% and 1.53% slower for virtual space and physical space monitoring respectively. And it used about 1.76% and 0.96% of single CPU time respectively. So I would argue that the overhead is quite low, and please note that the daemon is, in this case, conceptually scans all the memory every 5 milliseconds. And also users can still tweak each parameters for less overhead, though it will also means we will try some of the accuracy of the monitoring research. And how accurate daemon is? So unfortunately, there is no good and easy way for strictly quantizing the accuracy of monitoring research, but we can just say that the visualized monitoring research look reasonable, as you can show here. And also the pattern for MASIM shows expected ones with high accuracy, as you have also shown before. And I'd like to note that we can adjust the trade-off for high accuracy again, and though it also means that it can increase the overhead a little bit. And also I will show some more evidence on daemon accuracy in later slides. So next, let me introduce daemons. So we can now monitor the data access pattern of system with low overhead. What we will do, so what we kernel programmers would want to do with that. Some imaginable use of daemon is the daemon-based memory management subsystem optimizations, of course. Such a procedure would, it would normally like this. We will monitor the data access pattern of some memory range via daemon, and then find regions of our interest. For example, we would want to find hot or cold memory regions from the monitoring research, and then we will want to apply some memory management actions such as reclamation or using THP or not using THP, or promoting to DRAM and demoting to PMEM or such things to the regions. And so daemons is a feature of daemon that does the above works instead of you. So users will only need to specify to what specific access pattern of memory regions, what memory management actions such as reclamation or THP or such things they want to be applied. So this feature is currently merged in Amazon Linux, but not in mainline yet. I will post the patch set soon. So how to use daemons using its programming interface? It's very similar to monitoring, but it requires only one more step. So you should put the monitoring request in the daemon context struct again, as abovely explained, then create a new data struct called daemons object, which is standing for daemon-based operation schemes, and then specify the schemes that you want to apply to the system in there. So the specification of each scheme consists with 3 ranges for size, access frequency, and age of the interested region. In this context, the age means how long current access pattern has maintained. For example, if you find a daemon region that has number of access as 0 and age is 30 seconds, then you can say that the memory region has not accessed for last 3 seconds. And also you should specify what memory management action you want to be applied to the found regions. Then you put the daemons object in the context object and then call the daemon start. Then daemon will start monitoring as requested in the context and find the memory region of the specified pattern and then applies the action instead of you. All will be automated. So let me show you how you can really do this with live coding again. So I will modify the previously written working set size estimation module to reclaim memory regions of 4K or more size and not accessed for 3 or more seconds. So let me share my screen again. So I will do that in reclamation. Let's copy the module I have written before. So the change would be only creating a daemons object and then putting it inside the context. So obviously I need a pointer. And I need daemons pointer object and other marks, which I didn't explain about this. This will be explained in later. So just before calling daemon start. Great. So the first 2 arguments is the range of size. So we will find memory regions having page size or larger than that. range for the access frequency follow. So we want regions that didn't access at all. And we want to find regions that not accessed at least for 3 seconds. Actually, this is the number of aggregation interval, and the aggregation interval is 100 milliseconds by default. And the next argument is the memory management action we want to apply to the found regions. Memory allocation failure. And then set. Okay. So yeah, that was the writing of the module. So only 2 more lines of code has been written in Essential here, daemon new scheme and daemon set schemes. Let's test the product reclamation module now. So we will test that against the chaos access pattern which we can artificially generate with MASIM again. So it will do the same, have the same behavior, and by running the module and passing the PID of the MASIM to the module, we can expect that it will now shrink the processed RSS to 10 megabytes after the 13 seconds, because it will find only regions that didn't access for at least 3 seconds and then reclaim those. So let's do that. First. The workloads. And insert. Okay, so and we can show that the RSS is going down, and of course it can spike to 20 megabytes because in some point the regions that access before and regions accessed later are within the same time window for the 3 seconds, which need to be used before finding the at least 3 seconds not accessed. So the demessaging operation is not permitted. In this case, because we don't have much question in the working set size, because we have shown that before, there could be no program error, I guess. So yep, that was all. So let me start sharing my screen and go back to yes. So I have live coded and tested and found that the module is working as expected. So it has effectively found the regions that not accessed for 3 or more seconds and then reclaimed those. So the RSS size of the process has been reduced. To evaluate the demos, I have made 2 example schemes. First one is the ETHP, which stands for Enhanced THP. It applies the madvise call with the MADB THP hint for memory regions that real access has been observed, and it applies the madvise action for MADB no THP hint for memory regions that having 2 or more megabyte size and not accessed at all for 7 or more seconds. So this scheme is expected to reduce THP's internal fragmentation caused memory bloat, but still preserve some of the performance improvement of THP. The second scheme is PRCL, which stands for productive reclamation. It will reclaim memory regions that are not accessed for 10 or more seconds. So it's expected to reduce memory footage with minimal performance drops. And the result was as shown here. The eTHP has reduced 76% of the THP's memory overhead. In this context, I am saying THP as the THP with always policy. Meanwhile, the eTHP has preserved 25% of the THP performance improvement. And the productive reclamation scheme has saved 38.46% of memory with only 8.26% runtime slowdown. I'm not sure if I can say only, but anyway, the gain was bigger than the traded thing if we show only the number. So we can say that Deimos works as expected and seems effective for some systems. So this can also answer to the question how accurate Daemon is. Daemon is at least accurate for some of the system improvements like this. But I think we should ask a question again. Would that slowdown of 8.26% is really okay? So 8.26% slowdown of the productive reclamation scheme that we have just seen seems too huge for the production, in my opinion. Of course, it might be reasonable depending on the specific requirement, and we can again mitigate this by tuning the scheme to be less aggressive. For example, we can change the minimal age of the regions to be reclaimed from 10 seconds to 50 seconds or 2 minutes or in such a way. However, the Deimos scheme's tuning is also challenging because the tuning is needed for each workload and each system. And the parameters that we can use for tuning, namely the threshold of the range of size, range of access frequency, and the range of age, is not so intuitive for sysadmins. Some kind of auto-tuning programs can be a solution, and actually we have tried that, and so we have made a simple auto-tuner for Daemon schemes, and then we have used that to auto-tune the productive reclamation scheme, and it has achieved 24.97% memory saving with only 0.91% runtime slowdown, compared to the untuned productive reclamation, which saves a little bit more memory, specifically 38% memory saving, but incurring 8% runtime slowdown. I believe this can be much better than that. But couldn't we make the kernel to just work without such user space help? That was my question. So we have made Daemon reclaim with some enhanced feature of Daemons. So for such a production environment that prefer safety and stable needs more than performance gains, we have made Daemons to provide some additional features. The first one is time and space quarter per a given time interval. So Daemons, if the quarters are given, then Daemons use no more than the given time quarter of CPU time in the time interval, in given time interval. And also, if space quarter is given, then Daemons applies the user requested action to memory regions no more than the user specified space quarter. And second feature is regions prioritization. Under the quarter is applied case, so Daemons will not apply to all of the regions that having the user has interest, the access pattern of user's interest. And in that case, which region should be applied? Which region should be applied with the user-specified memory management action first? answering that, we have made this feature. So under the quarter, Daemon applies the action to prioritize regions first. And the prioritization logic can be customized for different Daemon actions in the layer that under the core part of Daemon, and therefore it can be easily extended. So in case of the reclaim, we use the older and colder pages as the prioritized one. And we finally provide 3 watermarks called high watermark, mid watermark, and low watermark with user-specified metric. This metric can be, for example, the free memory or CPU utilization or something like that. So we can deactivate. So in this feature deactivates the operation scheme if the user-specified metric is higher than high watermark or lower than low watermark, and we activate the scheme if the metric becomes lower than mid watermark but still higher than low watermark. This avoids Daemons using any resource on a peaceful or a catastrophic situation. For example, in case of the project reclamation, if there is sufficient amount of free memory, then there's no need to start the project reclamation. However, if it goes some down, then we should do some work, of course. However, if the situation is just catastrophic and therefore Daemon-based project reclamation doesn't work well, in other words, if it doesn't restore the amount of free memory to more than high watermark, then we just forget that and let the classic or regular reclamation logic to work. So we have evaluated the Daemon safety guarantees by applying the project reclamation scheme to apply it to the entire physical space with different safety guarantees. So we found that the smaller time quarter reduced Daemon's CPU usage and slowed down, as shown here. And also, by enabling the prioritization feature, we have found that it further reduced slowdown. So this means that we still need some tuning for each system, but the knobs we have introduced with these features would be intuitive for sysadmins. I mean, we can at least limit the CPU usage of Daemons, and also we can limit the amount of memory that can be reclaimed on the specific time interval by using the quarter, by using the space quarter feature. So using the safety guard features of Daemons, we have made Daemon Reclaim. It is a Daemon-based proactive reclamation kernel module that written using Daemons. So accepting the code for the module parameters for user-specific customization, it uses only 188 lines of code, and it aims to be used on production, in real production. For that, we have ensured the safety using the products and watermarks features, and the colors and watermarks can be tweaked via the module parameters, which contains about half of the source code. So future plans. First of all, I'd like to note here that these are only in brainstorming level, so I don't have a real serious plan for doing implementation of these, but I just wanted to share that earlier and get some feedback. So first, we can extend Daemon for some other use cases. So we can expand Daemon to be used for monitoring various address space, because I have shown you only the virtual address space, and also for some variety use case. For this, we need to implement new monitoring primitives for the use case. And because the primitives layer is separated from the Daemon's core logics, we can do that without many conflict or complexity. So currently the monitoring primitives currently the latest version of the Daemon in development tree provides the monitoring primitives for only virtual address space and physical address space and page granularity system-wide monitoring. And only the one for virtual address space is currently being mainlined. So more imaginable extensions would include more efficient page page granularity system monitoring because current page granularity monitoring primitives is only for proof of concept level. And I think the multi-gen LRUs, page table-based scanning, might be able to be used for this. And also we can extend for specific C groups and for only specific file vector memories only, and also for read-only or write-only access. And second possible future plan is improving daemon. So the daemon's accuracy and overhead could be more optimized, you might think. For example, we can use adaptive monitoring attribute adjustment and region splitting. In other words, we can find some regions that showing two stable access pattern or two unstable access patterns. In other words, we want to find some regions that some wrong monitoring interval and some regions that we are not really finding real access pattern in there, and then we can apply some more aggressive monitoring attributes there to enhance the accuracy. And also, I am thinking about remapping regions based on monitoring research to sort it by hardness could be helpful for enhancing the accuracy of daemon. So the daemon assumes each memory region will have some spatial locality. In other words, all the pages in each memory region are assumed to have similar access frequency, and this will be true for many cases, but we can also assume some worst case, which this assumption does not make sense. In that case, this sort of optimization might be helpful to still finding real regions, and for this, maybe we will need to maintain daemon internal address space and some translation facility for translating the address in the user's given address space to daemon internal address space. Finally, we could use daemon to improve memory management subsystems. I think daemon can be used to help some of the existing memory management subsystems. For example, we can use that to find THP promotion and demotion target regions, and also we can find better page migration target. In other words, we can find some cold memory regions and then try to migrate the cold memory regions first for compaction or CMA case, because the pages that not accessed frequently might mean that they would not be pinned in near future or for now. And also, I think we can use daemon to prioritize the LRU pages. In other words, making the pages in LRU list to be sorted in the real access frequency more proactively than current schemes. And also, I think we might be able to use that for tiered memory management, for example, the DRAM versus PMM problem. And the works could fundamentally be done in two ways. You might think we can implement a new subsystems wholly using daemon, like I have done for the daemon-based productivity reclamation, or we can modify existing subsystems to use daemon. Whatever way, if you have some opinion on preference of these two approaches, I'd like to hear your voice. And I guess it should be dependent on each specific case, of course, and maybe implementing new subsystems first and then get some users' feedback and then later modify existing subsystems would be also one possible options in my think. So final summary. The daemon and daemons helps you write fine-grained data access pattern-oriented lightweight kernel modules in simple way. And such modules could be useful for enhancing memory efficiency of today's systems. And there are many more things to do yet. So I'm looking forward to your contributions. I need your help. And for more, if you need some more information, please visit the project site or reach out to me via the email. Yeah, that's almost done. And before finishing this talk, I'd like to say special thank you to all the people who helped me doing this. Without these people, this work couldn't be done. And I think I might miss someone's name. So please blame my bad memory and forgive me or ask me some beers. After the pandemic is over, I will buy you some beers. That's it. And any questions?
Thank you really much. Thank you very much. I had put one question in the chat, and then we can see if there are other questions people might have. Have you measured, since you said you want to use this in real life production workloads, have you had experience using it on real production workloads, and other than just the CPU overhead, obviously by shrinking its working set, or reclaiming its memory, hopefully not from its working set, that might have some impact on the workload's behavior? And have you had a chance to see what the trade-offs are? If you can save so much memory, what does that actually do to the workload's runtime or page fault frequency, etc.? I'm sort of curious what your operational experience has been when using Daemon Reclaim.
So in short, we didn't measure the workload impact on real production world, but we have used some realistic benchmark and real systems. We have measured some impact, but that was not for real production. We don't have the data yet because we didn't deploy it. We didn't deploy it on real production yet. But what I can say is that under some realistic benchmarks, we have shown a minimal performance slowdown, and also we found that the slowdown can be controlled. So this means the runtime slowdown of the benchmark workload. And what we found is that the time quarter and prioritization is effective for controlling the amount of impact.
Great.
One of the things that I'd also like to point out to Ted's question is that we saw with some of the Java-based workloads, at least, is that Java does its garbage collection, so it keeps banging on some areas of memory, which it doesn't tell the kernel about, that it's a very low priority activity. So the kernel thinks all of that memory is important and it's accessing it all the time. But for the workload, that really doesn't matter. So deprioritizing that in some way is actually helpful.
So one question I have is more on the, I still don't see why the preference is doing this as a kernel module rather than from the user space. The daemon can provide the information to the user space, and in the user space I have more access, more flexibility to implement the feature. For example, as Ted said, I can look at the defaults rather than just some watermarks, and implement more sophisticated policies there. So what's the benefit of doing it as a kernel module?
Good point. So I think there are two different perspectives here. Someone prefers to do things to make the kernel to just implement mechanisms and export those to user space, and then policy is making on the user space. However, some people are still preferring doing as many as possible all the works inside the kernel space. And I believe that the two perspectives both make sense, because in some situations, the user space control plane might make sense if they have some time, resource and time for making the great user space policies. However, in some situations, in some environments, I think some people would have no such enough time and resource for user space investment. And for such a case, I think putting at least some of the features inside the kernel, which can not make optimal research, but at least some reasonable amount of benefit, would also make sense. So what I want to do is convincing both. So I believe that the optimal performance, optimal efficiency improvement could be done by only the user space control plane. I believe so. However, for some people that cannot spend their time and invest for the user space things, I think making the kernel to work at least a little bit better than before could also be helpful for some of the people.
So here, again, coming to the kernel module, as you said here, the sys admins still have to like set up, like configure even for the kernel module. I'm just wondering what's the, like, then we want some something out of the box configuration which might be helpful for everyone, right? That is the only way we want this, like, to be able, like, to be this part to be part of the kernel. So what's the, like, if we still providing knobs for the user space to or sysadmins to configure, we are still depending on the user space or human to actually set those knobs to able to configure for their workloads, right?
Yes, right, exactly. So the tuning overhead is still there, and we should need to still tune. However, by providing the knobs to be as much as intuitive for system administrators, I believe that they will be able to tune those with small amount of effort. And in this case, by using the time quarter and space quarter, people can start by using the kernel modules like this daemon-based project reclamation to start with minimal quarter, and after that they can start finding some better configurations. So I think the default value should always be minimal 1, and then they should find some better configuration on their own.
I have a couple of questions, and apologies if they are too simple questions. I'm not a memory expert in any sense, but I was trying to understand when you're reclaiming pages, I'm assuming you're either reclaiming read-only or file-backed pages, or if you're doing write-only or rather pages that have been modified, you're kind of swapping it to disk. Is that what's going on when you reclaim?
So there's no difference in read-only page and dirty page. So we only show the access frequency of the pages, and therefore there's no difference in read-only and dirty pages for now.
No, I understand for monitoring, but when you're doing reclaim, where you're saying you're reclaiming so much memory and you're saving memory, what are you reclaiming? Is it only read-only or dirty pages too?
Read-only and dirty pages, both.
Okay, so does it mean if I want to use it, I need to have a swap area?
So if you don't have the swap device on your system, then it will work for only file-backed pages.
Okay. Good to know. And then the other one is here you're saying time quota is 200 milliseconds per second. That seems like a lot. So what am I not understanding there correctly?
So can you repeat that again?
In the table that you have displayed, the second row says 200 milliseconds per second. Is that the amount of quota you're giving for demos to run? That seems like a lot of, like 20%, right, effectively?
So these time quotas are only set based on my intuition, and I wanted to explore how that works. And in this case, obviously the 50 milliseconds per second and prioritization enabled would be the best option here. And so, yeah.
Okay. I'm just asking from the context of, I'm kind of curious to see maybe after it's mainlined, how this could be used for like mobile devices where memory constraint is also there.
Yeah, of course. And the default parameters for the daemon-based project reclamation in current version of the patch set is 10 milliseconds per second and prioritization enabled. So by applying this minimal quota, I believe that using that on production would not impact the workload's performance, but it will still slowly reclaim some pages, and therefore, in the long term, I believe we will get some feasible memory saving. And Ted has asked, this is also the time quota on a single CPU, right? So on a 32-core system using 20% of one core, isn't that much? Yes, that's right. Exactly.
Thank you.
And also, if you want to, then you can also let Damon to do work for multiple contexts. And in that case, one thread for each context will be created. And therefore, if you cannot convince with the single CPU resource, then you can use multiple CPU either, if you can spend.
All right. Thanks so much. We're right about at time. I want to give people 5 minutes just to stretch a little before we start the next talk. So thank you very much. And I'm sure if you have additional questions, there was a contact address on the slide where you can reach out to Songjay for more conversation and questions.
Yeah, obviously.
All right.
Thank you very much.
Thank you. All right, we'll be starting in a moment. Sohail, are you ready?
Yeah.
Okay, great. Let me switch to your slides, and then I will give you presenter status. All right, so if you want to turn on your camera, if you're comfortable with that, I guess we can start. Next up, Sohail, and I apologize if I didn't get your name quite right, is going to be talking about hardware user interrupts as a faster way of doing IPC.
Yep. Yeah, you got my name right. It's Sohail. Hello everyone. As Ted mentioned, my name is Sohail Mehta. I am a kernel developer at Intel, and today I'm planning to talk about an exciting new technology called user interrupts. So at its core, user interrupts is just a really fast mechanism to do event signaling. So here are the goals that I have for today. The first thing that I'm planning to do is like provide some background or the motivation for coming up with this technology, what use cases we see this would be applicable for, and then give some overview of the software architecture and get some feedback from the community about like how this looks like and where we go from here. And feel free to interrupt me or post questions on the chat. I'll take pauses and I can answer them while we go through the presentation itself. I'm hoping this would be an interactive session, and so feel free to ask questions or provide comments. So what's the motivation for coming up with this technology, right? And so the main thing is we want to deliver events directly to user space, and doing that by bypassing the kernel. So we want really low latency, and we want user space to be directly directly receive events. Now, current existing IPC mechanisms and IO event delivery mechanisms, they have a bunch of limitations, like synchronous mechanisms like pipes or like epoll or reads. They cause you to wait. They cause you to spend a thread, and then they even cause you, like, they have higher latency, and they're inefficient. And like other mechanisms, asynchronous mechanisms like signals, they have even higher latency. So the only fast mechanism we have right now is polling, which is like really wasteful of the CPU. And so the idea here is to come up with a super fast and efficient alternative to these existing mechanisms. And the first implementation of this technology is in an x86 processor codenamed Sapphire Rapids. And so let's talk about what types of user interrupts are possible. So in all of this, the receiver is always expected to be a user space application. And so a user space application, similar to signals, it can receive user interrupts, and the infrastructure to receive, or at least the proposed infrastructure to receive all of this, is all common. So you can, so no matter the source of the user interrupt, like the receiver has it has the same common infrastructure. And so the senders, there could be various senders who could generate user interrupts. So the first one that is currently being enabled is a user-to-user IPC. So let's say you have a process running in user space, and it wants to send the signal to another process running on some other CPU. And both of them, they're executing some other code, and process A wants to send a signal directly to process B without going through the kernel. And so right now, so send UIPI. After doing some kernel enabling, send UIPI is a new instruction that would let them just directly send a signal without any any intervention from the kernels. You just execute an instruction on user space instruction on one CPU in user space, and you get an event delivered directly to another process executing in user space. And so the RFC patches for this are out. I have provided a link below, and so feel free to review the patches, provide any comments, if you have questions, feel free to reach out as well. Now, this is one source of interrupt, like a user-to-user IPC. Other source that we're thinking about is a kernel-to-user interrupt. Now, let's say you have a kernel event that happens on a different CPU than the thread that is than the intended process is running on. So now the idea here is that the kernel can directly send a user interrupt to the thread that is executing in user space without causing it to exit into the kernel. And so just as part of its user mode execution, there's a switch that happens, and it gets an event, it processes that event, and then it can go back to doing whatever it was doing. Eventually, and so the patches for these are in development, and I'm hoping to post them soon after getting some initial feedback on the user API patches. Now, eventually we see this technology evolving to have other sources of interrupts, and these could be anything that can generate a kernel interrupt today, right? And so these would mean like devices or any other external sources that could generate a kernel interrupt. They could potentially generate a user interrupt, and we could deliver those events directly to user space without any device driver or any kernel entity coming in the way. And so here are the use cases that I think, or at least I think are the relevant ones right now, and there could be a lot more in the future. And so before we go to the use cases, let's talk about how performant, like how fast is really this, right? And so there are two modes really where user APIs work. One is where you have an application that is running in user space and it's doing its own thing, and there is an event that gets delivered to it. Now, so in this case, since we avoid context switch at both the sender side and the receiver side. So let's say a sender, it executes the send you API instruction. The interrupt gets delivered to another process, the receiver, and we directly receive the event. And so this is really, really fast. Now there could be, and so just user API by itself is about 9x faster than event FT, and even much more faster than pipe or signals. Now we could have another mode where the user space doesn't have anything to do, or the application doesn't have anything to do in user space, and it wants to just block in the kernel and say that, okay, if you have an event for me, just switch me back in. And this is what I'm calling it as the user API block mode. So this, as expected, has a higher latency compared to the user API running case. But even this is much faster than any of the existing mechanisms that we have right now. And so over here, the application would be context switched back, it would be scheduled back, and it would get the event, and then it can, and it can act on it, and it can decide the next step of actions. And
so I had a question. Is it really much faster? That looks about the same as event FD, like maybe, I don't know, 10%, 5%?
Yeah, it's 10% faster than event FT. And it's like about 40 to 60% faster than others. But yeah, this one, we don't save a lot of latency. The only latency we save is on the sender side, right? Because the sender doesn't have to go through the kernel to generate the event.
Okay.
But on the receiver side, it's the same latency because you schedule the receiver back, and there's a kernel to user transition.
Yeah,
so it's still a bit faster, but not a whole lot. And all this is like
this is the full latency, right? From sender to receiver, right? That's what you're
right. So this is actually a ping pong latency. So both of these are a ping pong latency where from the sender to the receiver and from the receiver back to the sender, and in
Okay.
all of these cases.
Okay.
And so it goes a full back and forth cycle. I have more details on this in the backup towards the end of the slides.
Okay.
But
One another question, but it's okay if you want to address this later. I was just kind of curious what the use cases were, because having the user continuously running seems to be the case where it has the biggest impact. And what is the situation where a user space thread is constantly running, but also waiting for waiting for an API?
Right. So one would be where, say, if you have a worker thread that needs to, so you typically, like, you have a thread that is doing some work, and there is some other thread that is waiting for events, and then eventually that thread would send, that thread would make the worker thread do some work. And so here the idea is your worker thread itself is doing some work, but then if there is a high priority event that comes up, or if there is something that needs immediate attention, then it gets an API, it does the processing, and it then goes back to whatever it was doing previously. So that's the general idea, and there could be different ways in which people use this. Overall, it could be a combination of like running and being blocked. And so it's a very new paradigm in terms of programming today, right? Because we don't have, it's similar to signals, but this is really fast, and we were hoping that more applications would want to use it because it cuts down on the signal latency.
Yeah, so a question that came up on the chat from Florian, which was, how does this compare to a Futex wake? Is that something you benchmarked?
Unfortunately, no, I haven't compared it with a Futex, but I can definitely work on it. I can try to gather some data and post it in the mailing list. So the performance, so let me go to the slide that has the data. So this is the benchmark that I used. It's on GitHub, publicly available, called IPC bench. And it didn't have Futex, and so I missed comparing it with Futex. But I have provided links over here about what the enhancement is and how this, what we use to test all of this. I know it doesn't answer the question, but yeah, I can work on it and reply. We can discuss it on the mailing list. So any other questions, Ted, or was that the only one?
That's the only question on the chat.
Okay, great. So in terms of use cases, these are the use cases that we were thinking about. One is like just really fast inter-process communication, right? Where you just want to send data or events between two processes, and you can use this to do really fast IPC. Other usages would be like user mode schedulers, where you want to preempt threads, or you want them to do act on certain events in user mode runtimes. In future, like when we have device-based interrupts, these would be like for interrupt dispatch for network user space networking, where you deliver events to user space directly for these IO stacks. And do you have a question?
Yeah, I have a question. So I don't yet understand what this looks like in an application that wants to receive an event. Does it actually have to block in user space waiting for the thing, or would it jump to another instruction like in a signal handler?
So that's a really good question, and I have something that comes up in a few slides. If you don't mind waiting, then we would get to that in probably 10 minutes. Like I have a sample
Okay.
and an example and how it looks like. Sure. So so over here, like eventually for this to be useful, we would need to have like library abstractions and lot of other abstractions to make applications use this. And so we're thinking lib event and lib uring would be some of the examples. And we're just getting started with use case enabling, so we don't have any real world applications that are showing this. The only performance benchmarking that we've done is on this micro benchmark that compares these forms of IPC. And one thing that I wanted to check with all of you is if we have other suggestions for what type of applications would benefit, or what abstractions should we look at to make that would get the maximum benefit out of this. So I can take a pause here, and if there are suggestions, I can take them now, or you can post them on the chat and I can go through them later.
So have you thought about using this for host to guest wake-ups in a virtualization type situation, you know, like for VirtIO ring buffers sort of thing? Is that something that you've considered? I don't know if it's a good fit.
We did have a discussion about it internally, and the virtualization team at Intel has been looking at it. Unfortunately, I don't have much input on that part right now, but the virtualization team at Intel is definitely looking at that that's the exact specific use case that you mentioned. Yeah, I'm trying to think about what was the conclusion of that, but right now it escapes me.
There's another question in the chat asking, have you looked at using this to speed up signals, or I think even event FD implementations?
Yes, I did, and so I didn't include it in the slides over here, but the RFC link for the patches, that's where I try to describe, like I did try to go through event FD and signals, those exact two. The whole idea is, since it's a hardware-based acceleration, mapping it to existing abstractions becomes very tricky, providing backward compatibility for all of them, and like having user space have a consistent behavior across event FD and user interrupts would be tricky. And so eventually the current proposal at least has a new FD, which is very similar to event FD, but not the same. And I would talk about it in a few slides. And so maybe this is a good transition for me to go to the next slide. If there are no questions, then I can go forward. Okay, so this is the idea, or this is the software design that we're thinking about. And as I mentioned, this is quite similar to event FD. So the whole idea about this is opt-in via system calls, where a receiver thread, if it wants to accept user interrupts, it would register with the kernel, have everything set up, and then be ready to receive user interrupts. As part of the registration, it would get an user interrupt FD, which would be equivalent to an event FD. The only thing that it doesn't have is a counter. So it just gets an FD. It would share this FD with a sender, and now the sender would register. So in this case, the sender also has to register with the kernel, saying that I am a sender to this FD, and the kernel would make the connection between the receiver and the sender. And as part of the registration, the sender would get a handle back. And that handle is something that it needs to use with SendU API. So once all the registration is done, step 4, which I've mentioned over here, the SendU API, it happens all in user space. So it's just an instruction that gets executed, and you send interrupts just from sender to the receiver executing this instruction, and there's no kernel intervention at all. And so over here, the exchange or the authentication happens through an FD-based mechanism, but then the interaction happens through x86 instructions in this case. And so overall, the sender could be a user application, it could be kernel, it could be any other device. the example I've shown here is for a user-to-user user API connection, and the receiver is a user application. So this FT, the receiver could share it with some kernel entity like IOU ring, or it could share it with the device driver, and then eventually the plumbing would be made, and those agents would be able to generate events, and the receiver would be able to receive these events. Now, the idea here is it's a file descriptor based setup, and it's very similar to EventFT because EventFT is currently used for some of these scenarios. And so here is what the receiver APIs would look like. These are just prototypes, and this is just like the first stab at it. And I'm sure these would change over a period of time, and the naming and the parameters. But this is, I wanted to share this over here to give you an overview of what it looks like in terms of an application. And so here you have a user interrupt handler. And so there is a function, and this exact specifics of this function would be in the next couple of slides, but it's similar to a function handler, right? So you have a special function handler, you pass it, register it the kernel using a system call called register handler, user interrupt register handler. You register it with the kernel does the plumbing. After that, each task or each process gets a set of 64 vectors. So these vectors are nothing but priorities. Like say if you have multiple events happening at the same time, then one would get priority over another. And so you have a set from 0 to 63, and the application can choose which vector it wants to create an FT for. Let's say the application creates an FT for vector 3. And now whenever it passes this FT to any other process, whenever they generate an event, vector 3 would get triggered in the receiver. And so the receiver knows that, okay, this is the event that happened, and this is the sender that I had shared it with, and this is the event ID. So this can be used, the vector can be used as an event ID, it can be used as a priority mechanism, but that's pretty much the usage for this. And so we would share this FT using any FD sharing mechanisms. It could be like through fork or through any of the current like socket domains or PID-FT, GET-FT, any of the existing mechanisms, you can share this FT. And any sender that has access to the user interrupt FT would be able to generate this event. So let me pause here and like if there are questions. The next set of slides talk about how the sender can generate these events. And after that, I have a sample showing how this all works. Let me check the chat to see if there are questions.
I have a question.
Yeah.
So in the case of a receiver thread having multiple senders, so does that mean now the receiver thread has to go exchange this FD with all the senders? What optimizations are you looking at? I mean, how do you address
right,
that?
So
Yeah.
right. So now if you have multiple, so there are a couple of optimizations that we're looking at, and I have it in the opens. And so like if you have a sender and you want to share these, say if the sender is part of the same thread or same same address space, right? Same same process address space. Then we're thinking of a way where the sender handle that we talk about. So let me transition to the next slide. So we have a handle that gets created when the sender registers, and this handle can be shared across all the threads within the same process address space. Now there is an argument that like if I have multiple processes and they all want to share that same handle, then how do I go about doing that? And so one of the ideas that I was thinking about is like having an FT type of representation instead of a handle. This handle right now is specific to a thread, and let me, I'll go over how this works. But since you brought up the question, so this handle is specific to a particular task, but eventually we're thinking we could generalize it over like the same process address space, or it could be over like it could be shared between multiple processes.
Yeah.
It's okay if you're going to cover this later, but I'm really curious about the actual instruction level, what it takes as input. And I'm wondering how you would prevent the random user space from sending a user space API to another task it shouldn't be.
Sure. Yeah, I can talk about it. So maybe there are a lot. So I have a sample that I'm planning to go through, and maybe we can talk about it that time. So here are the sender APIs, right? And the sender, so continuing from the previous slide, like the sender receives the FD through some mechanism. And now what it does is it registers itself with the kernel. So you get a user interrupt register sender, you pass the FD to the kernel. Now the kernel knows that, okay, this is the receiver, and this is where this is how the plumbing, this is the intended receiver, and it sets up the hardware structures for this sender. And as part of the return, it sends it a user API handle. This is the handle that the sender needs to use now to generate the events for this FT. And so all the sender needs to do now is execute sendu API and pass a user API handle. Now this sendu API is a compiler intrinsic that is available in GCC 11. If you're using some older GCC, then you might have to use assembly hard coding to get this to work. But if you have GCC 11 or later, then you can directly use this compiler intrinsic and generate this event. And so this is how it looks like. Like this is the entire sample. This is the receiver side and this is the sender side. And so on the receiver side, this is how you would define a user interrupt handler. And I apologize if this font is too small. I had to reduce it just to get it to fit on the screen. And if you're really curious, then there are a lot more samples in the RFC series that I've sent out. And there's a GitHub page where it includes a bunch of more tests. And so over here, you have a user interrupt handler. You provide an interrupt attribute. This interrupt attribute is a user space interrupt attribute. And so if you compile it with an MUINTR flag, GCC would interpret this as a user interrupt handler. And it would do all the saving and restoring of state, there's a new instruction called a UIRET instruction that allows you to return from a user interrupt handler to your execution state. So all that is done automatically by GCC. And so all you have to do is define it. This is the proto function prototype, and just define it and do your processing in this event. And so over here, the parameters you get is a user interrupt frame. This is similar to like a signal frame that you would get. And you have a user interrupt vector. This is the same vector that the application had registered. And so now if you look at the receiver, it chooses a vector. Right now I'm choosing 0, but it could be any other vector. It registers the handler with the kernel, and then it creates an FT with vector 0. Now as part of the FT creation, it gets a user interrupt FT. And this is the instruction that is used to enable interrupt. So there is a global flag similar to the IF flag. Like on the kernel side, we have the interrupt flag that is used to enable and disable interrupts. User space can use the UIF flag, and the instruction for it is STUI, similar to the STIF instruction. And this is pretty much saying that, okay, I'm ready to receive interrupts. And the hardware knows that now it can deliver interrupts to this task. Over here, I'm using a threading example just to make FT sharing easier. But I create a pthread and over here, it starts execution. Now, over here in this example, the expectation is the application would be doing some other work. Right now, since this is for demo purposes, I'm just waiting for the interrupt to be delivered. But the idea is the application could be doing some other work, or it could just spin in user space. Eventually, it can even block in the kernel, but that would increase latency. Right now, this example, it just waits. Now, on the sender side, you register a sender with the FT that it would have gotten through some means. It gets a handle, and this is the instruction that I was talking about: sendu API and user API handle. And this pretty much generates this. This handler gets called. The vector 0 would get generated. and we would set user interrupt received, and we would break out of this loop and we would exit this function. And so over here, this is the compiler instructions, and this is the sample output that you would get from this. So I'll just pause over here. This is all that I had. And the next is like just feedback and questions about how do we go about enabling this feature but I would pause about, like, I wanted to get feedback on any questions you have right now on this. And does this answer your question? Sorry, go ahead, Flo.
Yes.
Is
That's
the,
good.
is the registration of the handler, is the handler just a thread local thing or task local thing, or is it process global?
It could be any of those as far as I understand. So the handler, you mean when you register and how the kernel stores it. So right now the kernel stores at a task local or a thread local thing. So every task that wants to receive an interrupt would have to register its own handler. And it could use the same handler, but then you need to be careful about how if you want this to be re-entrant and how you define it, but it's up to user space. The kernel, all these registrations happen on a task specific level, at least on the receiver side.
Okay, that also means that I need a descriptor for every task. A file descriptor.
Right. So for every specific event that you generate, because this file descriptor would only generate interrupts for this specific event, for this specific task and this specific handler.
So
now,
one of the questions on the chat was, could this be used for a broadcast mechanism where there are multiple receivers? And it appears the answer is not really, because you have to have separate handles for each receiver. Is that correct?
Right. So this will definitely not work for a broadcast mechanism. If you want to do a broadcast, you would have to pretty much iterate over all the receivers, which would kind of defeat the purpose of the broadcast. But even though it would still be a lot faster, it would super fast, and so the dispatch latency for this instruction is not very high. So one thing that I didn't mention earlier is this is an asynchronous mechanism, right? Where the receiver could be running, it could have interrupts disabled, it could be doing something else, it could have been context switched out just because of scheduler, some other priority task running. And so the sender doesn't need to wait for this instruction to return. It executes this instruction and it can go ahead, and at some point this event would be delivered to the receiver when it's ready to receive it.
I'm thinking about using that to implement something like a condition variable. But given that you have to register the thing on the waiting thread, it probably doesn't really match that kind of programming model.
So the main reason we're not able to share it between processes, similar to how you can do it for a signal handler, is because all the underlying hardware plumbing is based on a per thread MSR. And so for the hardware to distinguish between which thread is running and which thread is not, and how to deliver those events is quite complicated. And the kernel is not involved in the fast part, right, where you generate the event and the hardware just needs to know where to deliver this. And that's the main reason we're not able to share the have a common receiver, shared pool of receivers that can receive these events.
And you need to do actual work in the kernel to set up the receive operation. So it's not something you can do once, conditional variable weight function is called. You have to really do that upfront and to amortize the cost, right?
Right, because in this case, one is like applications might not be aware of, like they need to be compiled in a specific way to receive interrupts. And so we can't expect, like we don't know if all we can't just enable these for all applications that are not even aware of user interrupts. And so like it is a registration that has to happen before to be able to bypass the kernel. Like the kernel does the authentication, it does the setup, but then the hardware needs to do the IPI. Now, if you include system calls at during the fast part, fast part, then this pretty much loses all the benefit that it has, right?
But would it be possible to emulate this on older hardware so that you can use an unmodified application running this code, and then the kernel just does this by trapping the instructions?
Yeah, that's something that I actually wanted to get feedback on. So like how do I so like eventually like other architectures or older architectures, what like would we want to run this on those, and then how do we go about designing this and having this compatible? Because like you would have to have a special handler and you need to use special instructions. Like this call would definitely fail on older architectures. So initially, at least the idea I was thinking is, if this call fails, then applications have a backup mechanism, like they could use event FT or any of the existing mechanisms. But I wasn't sure if that would be a good way to approach this, or have like this all compatible, like everything compatible just in a slower mechanism on older architectures.
Yeah, I think both works. I would go for the emulation on x86. I think it's probably not a good idea to implement this on other architectures, because if another architecture implements something like it, it's probably not compatible. So they would have slightly different thing. They might have a different layout for the saved register structure or whatever. And then we will do it once another architecture adds this feature. But as soon as this is nailed down in the instruction set, we could easily emulate this in the kernel if we decide that's a good idea.
Right, and so the system calls, like at least right now, I've designed it based on how x86 does this. So the part that I wasn't sure about is, like, do we try to make the system calls as generic as possible? But then how do we know how other architectures would go about doing this? And so we have the risk of like just kind of having other set of system calls that would be needed in the future.
So there are a couple of questions on the chat, if you wanted to take a quick look, or I can read them to you, whichever is easier.
Yeah, sure, go ahead.
So first question from Samarath. Can we use this mechanism to wake up a kernel module?
No. So at least so that module should be running, or it should, like, maybe yes and no. So there is a mechanism right now, at least the idea is it's a ring 3 interrupt receiving mechanism, where you would receive this interrupt when an application is executing in ring 3, and the hardware is built for that. Now at the kernel side, if you want to wake up a kernel module using this, I don't know if this is the best mechanism to do. I'm guessing there are other mechanisms that can be used to like just a syscall, or just some other mechanism. Like the main idea we're trying to do here is trying to bypass the kernel for event delivery. And so a users, like it's a pretty much user space enabling. I don't know how this would work for waking up a kernel module.
All right, quick question from Greg. Clang support?
Not yet. So we are working on that. This is like the first thing that we got enabled is with GCC. And we have internal discussions going on how to get Clang support to work on this. But I haven't tried it with Clang. Maybe Clang might have looked at how GCC has done it and tried to implement the MUINTR intrinsic, but I'm not sure. I still have to check on that.
Another question from Greg. Do you have workloads in mind that will benefit from this?
So I don't have specific workloads. The one that I talked about here is like user mode schedulers are one, and just really fast IPC. But this is one space where I'm actually looking for input. Like if there are use cases that people think would really benefit this would benefit the use cases. And this is the right phase because the first RFC is out and we can start interacting with the those users or usages to get this API right.
A question from Lucas. Can you tell me more about how this instruction works at a hardware level?
Sure. So I have a few backup slides and I can go over those. We can have a separate. I'm not sure if we have a lot of time to cover those. I actually wanted to get some feedback on this, but I can definitely go over them if we get through this slide, and I can give you some input on how the hardware works. But
Yeah.
if you can
so
download this,
I should note that I did post in the chat a pointer to your patch submission. And if you go to the download link on Plumbers, Linux Plumbers or Kernel Summit track for your talk, there's also a link to the lore.kernel.org of your patch. And I believe there's actually a fairly good amount of detail in the patch submission about how the instructions work. And so if you want to just simply refer people to the patches, that's fine too.
Okay.
I did kind of skim through the patch that Ted pointed us to. It still wasn't clear how we're preventing a sender from being able to send it to any other random task, and also how does it identify which CPU it needs to send it to if the task is running. And one additional question was, you said you weren't aware of the use case in mind, but I'm hoping that hardware engineers who added this instruction at least had some use case in mind.
Yeah, there definitely use case. Like I just don't know the exact use case where. So we are in talks with a lot of customers about where this would fit in their usages. One obvious thing is where we have user mode runtimes, right? So this could be like the Google Go runtime, or like Oracle has user space. User mode threading schedulers and libraries, and so those are the places where we think this would definitely have some benefit. It's just that I don't have something enabled to show where, okay, this is the benefit that you see on a real world workload. This is still like a work in progress, and we would get there eventually. And overall, longer term, like having devices generate interrupts and delivering it to user space, user events is definitely a plus. It helps with scalability in terms of how event dispatch and processing works. But those use cases would be developed over a period of time, like much later. And so right now what we have is user to user IPC and kernel to user event notification. And the question about having this, preventing others from sending it, that is the main reason we have this FD, right? So you have an FD that you create, and the receiver sends this FD only to tasks that it trusts. And it could be within the same process address space, or it could be across process address space to processes that it trusts. And so only senders that have access to this FD would be able to create this plumbing and would be able to use this handle.
Yeah, no, I understood it at the API level. I was just wondering how it's enforced at the hardware level. But if it's too much,
For the hardware level, there are MSRs that this instruction would use. And those MSRs would be programmed only, and those MSRs have a table and they have a routing to the receiver where it would only point to the accurate receiver. Now, if the task hasn't registered or if it tries to use some invalid handle, then the hardware would complain and generate faults.
So yeah, I'm from Oracle, so we have that use case where potentially, the DB is going to be doing user land threads, and that's where they're looking to use this. So I'm going back to your previous slide. I'm mainly interested in this whole receiver-sender association. How will this scale when you have many senders? So one thought was, if you can allow the receiver to directly register into the sender's table. I know you didn't go into the implementation detail so much. The sender has a table, right? UITT. And the receiver doesn't have to have an FD, right? So if the receiver can directly register into the sender, and you have a common sender table with, typically you have many senders, just like in a signal and situation. You have many processes which can send a signal to any thread or process. So yeah, that needs to be, otherwise it won't scale when you have thousands of processes that you have to send your FD to.
Right. Yeah, and that is one of the ideas I had over here. Like one of the opens where like a sender creates a user API handle. Now this handle could actually be created by the receiver itself, right? And so a receiver creates this FD. It registers itself as a sender, and so this would just create like a self API type of mechanism. And now you have a user API handle that can be shared across threads of the same process, and they don't need to register themselves. They can just do a user API based on this handle, which is global to the address space. The idea you are suggesting could be extended to like across processes as well, where you have multiple processes and they all want to share the same sender table or the sender handle, or this handle you want it to be global across a set of processes. And that's where I was thinking if we can have like a place or a mechanism. And so this is still an open, I was thinking like if there's an FD, just one FD, which gives you access to the whole table, where you get access, you inherit all the connections that you had previously made. And this could be like a named FD, like it could be in a named pipe or something where you can just open that pipe and you get access to all the senders. The entire sender table gets inherited. But this is still a work in development, and I'm trying to figure out if there would be benefit for doing this and what would be the complications. Now, since this is a hardware level mechanism, sharing this handle across threads or across processes involves a lot, makes the kernel implementation somewhat complex, right? Because now you need to mimic changes made by one thread into changes across all the threads that are sharing that. And so when the table that you have that grows or it changes some attributes, then you need to replicate this across the threads that are using this. And so this, I'm actively investigating this, but I just wanted to get a feedback on whether this would be useful. And I'm guessing the answer is yes. It would be helpful to have this handle shared across threads and processes rather than having a per thread mechanism, right?
Yeah.
One other open that I had, so before, and I know we're getting close to the time, one is whether having this syscall and FD-based approach works because this we could change the specifics of how this is defined. But one major feedback that I was looking for is whether having like a syscall and FT-based workflow, is it a good idea or no? And so if anyone has comments or anyone has any feedback on the overall approach, I mean, please let me know.
File descriptors.
Yeah, it would definitely help in validating who has access rights and all that, right? If you were, let's say, if you go to the model we were discussing just now, where the sender has a table which you want to share, and if it is an FT-based thing, then you can check who has access to that, and only those threads will be allowed to write into it. That might be.
If there's an opportunity to use this to implement condition variables in glibc, for instance, then the file descriptor-based approach is a problem for us because for compatibility reasons, we can't keep open the descriptor and we can't add unexpected file descriptors in the core runtime because applications, well, don't expect that. And in this case, if it turns out useful for anything in like pthread condition variables or certain types of mutexes, then we would need a different mechanism for managing the registration.
Okay. Okay. Yeah, the main reason for having a file descriptor is like, do we have inbuilt authentication mechanisms across processes? And so would there be any other mechanisms to authenticate, whether like where I want to give up one process wants to give permission to another process to like interrupt it or do something about it, right? And so do you have suggestions on what other mechanisms would be?
I was wondering if you need that within the same address space, same process.
Right, within the same address space, we don't need to have an FT, and we could have other mechanisms. But like I wanted to keep it consistent between whether it's like the task is as part of the same address space, or it could be different, and have a consistent model across both of them.
Understood. Thanks.
So I had a question that related to the sharing senders across multiple processes. Can the page that contains that table be mapped? I understand that there's an MSR register that is as a pointer to the page, which is where the table is, but can that page also be mapped into processes page table or multiple processes page tables and then manipulated in that way, or not?
Yeah, it could be. So that is definitely possible, where you have so you can sharing the memory is okay. Like you could have some abstraction for that memory, and then you share it across processes, and it could be mapped across all those. The complexity was from like where this MSR is pointing to, and we also have a place where we store the size of this table. Now let's say the size of this table grows from 4K to 8K, and now you need to propagate that size change across all the threads that are sharing this table, and that definitely is possible, but it would add somewhat complexity into the kernel. And so I didn't want to do that unless we have users for it, or unless people want it to happen. I didn't want to add that extra complexity into the kernel. Does that answer your question?
Yeah, fair enough. Thanks. So we're almost at time, and I again want to give people a quick 5-minute chance to do a stretch break. Are there any final questions?
So sorry, Ted, just before we go, I had a final question for the group. So right now, user interrupts don't interrupt existing system calls like sleep or read or any other processes or any other blocking system calls. And so one feedback that I wanted is whether we would want to interrupt, like say if a process is sleeping and it gets a user, it calls a sleep and it gets a user interrupt, do we want it to be interrupted? Like a signal, you break out of the syscall, and you get an e-inter signal and you try to restart the syscall, like you have a SA restart type of mechanism that does the whole thing, which happens with signals. Like, do we see usages where this would matter or this would be important? Okay, I guess we can have a separate discussion for this, or separate conversation over the mailing list. Ted, one other question that I had is, we have interest in the hardware architecture, and so is there a possibility of getting a BOF session for this, or should I just go through a hack room and just for
Yeah,
the
so
people
I
interested?
believe all of the BOF sessions have been scheduled, so probably your best bet is to grab one of the hack rooms and announce a time, maybe after all the major sessions have happened, or tomorrow at some point. So I think grabbing a hack room is your best bet at this point.
Okay. Yeah, I can chat over, like we can discuss this over the chat. I don't want to take up the presenter's time. So for the hack room, we can discuss it over the chat, and we can come up with the time. Thanks.
Okay, thank you.
Yeah, so thank you everyone. Yeah, yeah, go ahead, Stan.
All right, so we'll take a quick 5-minute break, and after our 5 minutes of break, we'll be switching to the last talk, which is the fast NVMe pass-through. I believe I did see Kanchan in the room a moment ago. Kanchan, I did update the slides in BBB about an hour ago, so they should be up to date.
And Ted, are you able to hear me?
Yes, we can hear you.
Perfect. I just survived a system crash and I replaced my system, so I was not sure whether I'm audible and I'm visible. So looks like
yeah. So we can. You're audible. I don't see your video at the moment.
okay. I'm going to switch it on now. Do I?
Yep.
Look?
Well,
Fine.
yes, you're visible.
Thanks, Ted. Thanks a lot.
All right. All right, so we will start at the top of the hour, which is now 4 minutes from now. And at that point, I'll switch it over to your presentation.
Thank you, Ted. Sure.
Thanks. All right, we're at the top of the hour, so let's get started. Ken-chan, if you're ready to get to present, we'll start your session about building a fast NVMe pass-through.
Thank you, Ted.
All right.
So can I get started?
Yep, I will give you presenter status in just
Okay. So I think I need to pick it full screen, and that would be the way to go ahead, right?
So if I've made you the presenter, so you should be able to move through the slides using the arrows at the bottom of the slide area. You should see left, right slides. And if your mouse is over the body of the slide, we will all see a little red dot where your mouse pointer is.
Perfect. Okay.
Yep.
So thanks, Ted. Hi, folks. This is Kanchan, and today I will talk about building a fast path to NVMe storage device. So the whole talk is at high level. It is divided into 3 parts. So first we will look at what is NVMe generic device and why do we have it. The second one would be about turning the IOTLs async. And the third one would be using the async IOTL and building a fast NVMe pass-through. I am not calling it async because it is little more than async. So the word here is during pass-through. So this would be the outline, and yeah, before we get into all that, so I feel the need to add a thank you note. So the first one is for the IO-ring for being around and being extensible, and to the maintainers, Jens, Christoph, and Keith specifically, and the mailing list for all the directions and the feedbacks that we have received so far. I can't imagine this work being possible without all this. So let's start with this screen over here, which shows a block device, which is NVMe 0N1. And if we look at the capacity of it, it shows size 0, while this device is around 12 GB of size. So what is happening over here is that the kernel did not like something about this device, and it decided to create a block device with 0 capacity. And there are other cases when a block device can be marked as read-only, or it can be marked as hidden. And the reason is that that the block abstraction is subject to conditions and rules, which makes sense because I mean, generally it happens when basically kernel finds a device which may be having a feature which is probably too new to be supported. It could be too uncommon to be supported, or maybe it requires, let's say, too much of churn in the code, and maybe it doesn't really make sense to support it. But then but the bottom line is that we may be having I mean, the outcome of is that we may be having a device which is having a block interface, but it's not usable. And the example here, why it happened over here is because this particular device was having a LBA format, which is 4 KB plus 8 byte, while the other one was recognized fine, but the first one did not. And it can also happen when we have new device type, new command set types like KV in some GNS devices, perhaps. So when we have such kind of situation, so the block interface essentially fails, and it's reasonable. It's fine to do that. But in order to be able to use the device, what we propose here, or what we actually have now already in the kernel, is a new kit on the we don't call it new kit on the block, but we call it new kit on the CAD, because this is a CAD interface. What you see over here is NG0N1 and NG0N2. So this is what we refer as NVMe generic device, and it's a CAD device. So if you look at the big picture over here, at the top above the kernel, we see three interfaces. The first one is file IO. The second one is raw block IO. The last one is the SPDK one, and we can call it a kernel bypass path. And the third one, which is shown by green color over here, this is the path that we're talking about over here, generic device path. So you could see that if we look at in the kernel, this is having a CAD interface, and NVMe would be supporting it. So we have the same for SCSI as well, SCSI generic device, and now we have added this in the NVMe as well. So it's a per namespace CAD device, upstream from 5.13 onwards. It's always available, not subject to rules. And similar to SPDK, it is lean. I would say devoid of abstractions, and devoid of rules, basically. And unlike the SPDK, it is an in-kernel path, and this could be useful for trying out new features. And that's, I think, similar to SPDK. Now, if we look at what all we can do with this device, so the first thing is that the NVMe client can enumerate it, it can list it, and it can do all that it can on a regular block device. This is also usable over NVMe over fabrics if we enable the controller pass through on the target side, and then we can see this device on the initiator and same NG0N1, and we can start using it. And as far as IOs are concerned, so application can send any NVMe command via pass-through interface. So what you see over here is the FOPS of this device, and you see here the function pointers are for ioctl. So the current transport is via ioctl, which makes it little less useful. So we thought of having a async transport for that, and I think the first shot that I gave to it, it's I think it's too trivial to be mentioned over here, but yes, I think I tried to plumb it, and turns out that Jens had already set about turning the ioctl async in our Uring way. So we will be talking about that in the subsequent slide. But yes, the bottom line here is that the future transport for this particular interface gonna be Uring. I think I will be skipping most of this slide, which is about touch base with Uring, and for this audience, I think this is not relevant. I only kept this. This is for the sake of completeness here. Maybe only thing which I should mention here, because it is still relevant when we talk about async ioctl, would be the communication interface between the user and kernel. So the backbone here is a pair of ring buffers, which kernel creates and uses space maps, summation queue and the completion queue. And the programming model is that the application picks a SQE from SQ ring. It can populate it with, depending on the operation, read, write, or whatever. And it can repeat this process. It can pick little more and make a batch basically. And once the batch is ready, it can call a IO ring enter system call for the whole batch, and it can submit it this way. And at some other point of time, it can read the completion from CQE, from the CQ ring, because kernel will make sure that when it receives the completion, it will be posting a CQE over there. So the programming model is just that. I mean, to put it in a simple fashion. Of course, IO ring offers a lot more than that, and this has been described in other talks in much better way, I would say. So let's get into the async IOCTL. So we are going to be seeing the user interface of the async IOCTL first. This is not called async IOCTL at this moment. It is called uring command. And it is IOCTL-like facility, yes. And the operation code for this is IO ring OP uring command. So this is the first thing that application need to do. It should use this opcode. The second thing is that it needs to use a different SQE. The layout of the SQE is different. This particular SQE was introduced by Jens only for this case. So it's called command SQE or CSQE in short. It's similar to the regular SQE with the difference that it has 40 bytes of free space. And this 40 bytes of free space is called payload. And uring does not peek into it. The idea behind this payload is that the IOCTL user, that means the application, can put whatever it wants to put into this. And the IOCTL provider, which would be in the kernel, could be file system, block layer, or maybe NVMe driver, that would be operating on this payload. So it's kind of a private affair between the IOCTL provider and the IOCTL consumer. While uring's job would be to pick it and transfer it from the user space to the kernel provider, the IOCTL provider, I mean. And the idea is that, so typically when we think of IOCTL, it may require the IOCTL command, which is the last argument over here. It may require some storage. And for async case, we would want this storage to be persistent as long as the command is not complete at times, I mean. And when we do that, we could use this 40 bytes of space rather than allocating it separately, I mean. So we could put this whole thing in line inside this payload. Maybe the other extreme could be that if it is larger than 40 byte, we could allocate it and we could put a pointer of it inside that. That would be second way to go about it. But as I said, that there are other ways to go about it. So essentially, it's just between the provider and the user. And if you look at the program over here, so it is showing that we have a we basically pick a command SQE. Actually, we call a SQE. I mean, we pick a SQE and we start calling it command SQE, and then we set up the uring command opcode into it, and then we populate the payload into it. And once we have done it, then we submit it in a regular way, and we also complete it in a regular way. So that part is not changed at all. Going further, now we are going to go into the kernel, and we are going to see the communication model between the IO ring and the IOCTL provider. So here, IOCTL provider is expected to implement a new method, which is called uring command. It's a file operation. And if you could see, the first argument here is a new structure, which is called struct IO uring command. So that's another container which IO ring is going to be preparing based on whatever information it received in the SQE, in the command SQE, I mean. And this is going to be a cardinal structure because this would be used for all the communication between the IO-ring and the kernel. I mean the IOCTL provider. So if you look at the sequence diagram over here, so IO-ring is going to submit the command by calling this method uring command, and it's going to pass this container to it. Now IOCTL provider, it may complete the IOCTL instantly. If it does, yeah, it will say that I'm done. And if it cannot complete, if it thinks that it needs to do a little more, it can say that it can return EIOCB queued. And whenever it is done, when it receives the completion and thinks that I have done all that was required, it's going to call this new API, which is exported by IO-ring. It's called IO-ring command done. And in this, it's going to return the status, which is the second argument over here. Now, once IO-ring gets it, it's going to post a CQE, package this result, and then going to post into CQE, and then the whole thing is over. So that's the model over here. Now, if you look at the use cases of it, so the original patch set from Jens, it has a bit of network and bit of storage. Storage part was mostly to, I think I showed the example over there. There was IOCTL, BLK, BSG get size, primarily to test things. While there is also something on the network side. As for storage, I think it can also be useful for the file systems user. I remember Derek once talking about using it for XFS scrub because it is a heavy user of IOCTL. Then we see that it can be useful for the pass-through path. So pass-through is already a lean path to the storage, but because of IOCTL, it was not useful. So we see that we could make that path useful by leveraging that. And in rest of the slides, we are going to talk about that. There could be more things. I think IOCTL, because it's kind of a catch-all system call and it's being used for a variety of purpose. So there should be more things which probably can be built over it. But then, yeah, I think I would be happy to hear from the group over on this. And yes, now let's actually see how can we wire up the uring pass-through. How can we move from an IOCTL-based pass-through to uring pass-through? And before that, yeah, so NVMe pass-through. For folks who probably are too busy to look into this, so it's like it's a mixed package. It has its good, it has its bad. So we see this picture here in the left-hand side. So we already have a bunch of abstractions layer in the kernel. They are stacked upon each other on the storage device, and each one is having its own purpose and utility, and it's great for general purpose. But one of the side effect of that is that if we have a new device feature and a new interface maybe, and we want to make it reach to the user space, we have to move all these letters of abstractions, and it may take some time. It may take some kind of consensus building, and at times maybe the device interface it's a very subjective to the device feature. It's not a general statement, but yeah, depending on that, we may have to when we are trying to move a device interface to the user interface, we actually have to craft opaqueness to it so that the interface can be used in future also, maybe for some other feature, and that becomes tricky at times. So this eventually presents some challenges for people who want to try out new things via kernel faster. So with the pass-through, we already have kernel already is providing a way to skip all that, and there's a way for these new features to be consumed in native way at least, and with those new features, we do not really have to do a lot of plumbing inside the kernel. We don't really have to build the blocks generate commands, in-kernel users, simulations, user interfaces, which are definitely tricky. And user space can probably start using it, maybe build some user space file systems, DB, which would be domain specific, yes. So all that is possible, but then all that is spoiled by the fact that the pass-through travels via blocking IOTL. So that's the motivation behind turning the existing pass-through. And now we see how do we wire up the async IOTL into NVMe. So if you look at the current NVMe IOTL operation, it's like a forced behavior. It is a forced sync over a naturally async interface. NVMe is the interface is actually same like IURing, right? We submit the command into NVMe submission queue. V means host, time t, and device will take some time to do whatever it's required to do the submission, and then it will say that I'm done. And then at some point of time when device has the completion, device would be posting it into the completion queue, which again is shared between the host and device, right? So completion is decoupled naturally at the interface level itself. And currently NVMe driver implements the IOTL by forcing the submitter go into a blocking wait. And when we move from the IOTL to URING command, it's only about decoupling the completion from submission at high level. Just that, no blocking wait. And but then, yeah, there are things which are tricky here. So one of the tricky thing here is what I call async update to user memory problem. So at times, IOTL may be having some user specific fields which need to be updated during completion. It is not just about returning the status, but also about updating some fields which are residing in the user space. And such if we have such field, at least in the pass-through, we have that field all the time. So when we have that thing, it becomes tricky to access it when we are receiving the completion and interrupt context, because it's not safe to access those. So we had to introduce something more there. So thankfully, we have the taskwork infra in the kernel, and IURing already has the helper functions for that. So what happens here is that the NVMe driver, when it receives the completion in the interrupt context, it knows that it can't touch those fields. So what it is going to be doing is that it will be preparing a callback function, and it will supply this callback function to IURing. And the IURing will schedule a task work, and when the task work fires up, it's going to execute that particular driver callback function. So what the thing that you see in the yellow color over here, just before that you see IURing command complete in task. So this is the new API that we had to introduce in the IURing, and with that we go about solving this problem. Now let's look at the example of a NVMe pass-through. So here we are talking about reading from generic device NG0N1. So if you look at the code over here, yes, we start it by, of course, opening the device. We get AFD. Then we allocate a pass-through command, and then we set it up. It depends on what do we want to do with the pass-through command. We will be setting up for read or write, or probably for some other actor like maybe I would say zone management, bad example, but yes. So yeah, once we have set it up, then we are going to fetch a CSQE. Once we have a CSQE, we are going to set up the pass-through IOTL, that pointer that we actually allocated inside this particular inside the payload of the CSQE. And once we do that, we of course also tell the IOTL code, which is the pass-through IOTL code over here, and then we send it down. And And yes, we will read the completion in a regular way, and that would be the way to do a async pass-through read. So this whole thing, of course, it introduces a couple of possibilities in general. And if I talk only with respect to Joan devices, it's going to be introducing at least two new things. One is that with this we can actually do asynchronous Joan reset. So Joan reset currently happens via Joan management IOCTL, and Joan reset is similar to actually a trim operation, but then it is kind of mandatory for Joan devices, because with the Joan devices the host has to do the garbage collection, and if it does the garbage collection, in order to reuse the Joan, it has to issue a Joan reset. So it is no longer optional like trim operation. So this is going to be used a little more frequently. So I think this could be useful. And the second thing here is that we could send the Joan append command at multi-QD. So Joan append currently is usable in the kernel, but we do not really have any user interface for that. So this could be one way to issue the Joan append commands at multi-QD. Going ahead, so once we think that we have sorted the async one, it's about async. Yeah, of course, it's a first step. It's a necessary step, but it doesn't have to be the only step, because NVMe is talking to IOring, and so we feel that there's a room for adding more goodness. IOring already has a bunch of features for faster IO. Some of it I have listed over here. Of course, it's not a comprehensive list, but then I think it is the main some of the main items. And if you look at the table over here, so here in IOring, yeah, of course, IOring has all of it. While the URing pass-through, the first two features, register file and SQ poll, they become automatically available with the plumbing which I described in the previous slides. While the fixed buffer and async polling, that's not going to be available automatically. So we are going to be seeing what can we do about it. So first is the fixed buffer. So fixed buffer helps because this is about pinning those user buffer once and reusing it subsequently. So this is going to reduce the per IO cost of pinning and unpinning. So this pin user bases, I mean. And the way to do it currently is that we call IOring register. We pin the n buffers upfront, and IOring sets up the BioVac for these buffers. And when the IO happens, of course, I need to use a different code because this IO is somewhat different than the regular IO. So it's called fixed buffer IO. So it will be specifying a new opcode, and then it will also be telling which buffer to be used. It can be specified by index, and that's how IOring currently uses the fixed buffer infra. And for URing command, we add a new opcode, which is URing command fix. Buffers for the pass-through, they will be registered with the same mechanism. And the index is also passed in the same way. All IOring has to do is that it has to make the infra accessible for the driver. And in the NVMe, we are going to use that infra. So rather than doing a pin and unpin, we are going to talk to IOring, get these, pass the buffer and buffer index. Actually, we pass the URing command here. It has all the information. And then we get the BioVac. And once we get the BioVac, we are going to be setting those pre-populated BioVacs into Bio, and then we will send it down. And that would be the way to have it up. And we don't really have to introduce a new IOCTL opcodes for this. We could use the same IOCTL because we are anyway using a different opcode in the IOring. So that itself is enough to differentiate between a regular pass-through and a fixed buffer pass-through. And now I am moving to IO polling. And before we talk about pass-through polling, let's see what do we already have in kernel as far as IO polling is concerned. So IO polling, yes, it's the primary use here is to enable the interrupt-free IO, which could be particularly useful when we have ultra low latency storage devices, and then the essential way to tell the completion that has been interrupted. Actually, it starts being a non-trivial software overhead for such devices. So polling is one of the way to have the interrupt-free IOs. And what we already have is that we have sync polling. In the sync polling, we submit the IO and we spin for the completion in the same syscall. So it's a submit and spin. And read v2 and write v2 can be used here. We have hybrid polling, which is about relaxing the CPU. The block layer has that infra, relaxing the CPU by sleeping in between. So the scheme would be like submit the IO, sleep for a while, and then spin it. Try to predict maybe how much time it can take, or maybe user can specify that. But yeah, that's all about hybrid polling. The third one here is the sync polling, and this one is about decoupling the polling from submission, and this gives third choice. Third choice, I mean, beyond spin and beyond sleep. Now, application can submit some more IO while it has submitted one IO basically, or it can execute some app specific logic. And the way to enable this in IO-ring, I think IO-ring is the only one which provides it, is to set up the IO-ring with IO-ring setup poll, and all the IO to such ring, they become polled. So this is all we have currently in the kernel. What we do not have is that IOTL polling or pass-through polling. Maybe it never made sense before. And we are talking about having it up now. So this is the way how we can go about having the pass-through polling. So what we see over here in the middle is per core software queues, which are SCTX in the block layer. They are mapped to the HCTX, and the HCTX, they map to the NVMe submission queue and completion queue pair. So you could see that there are 4 HCTX, each one is mapped to one pair. NVMe at the protocol level, it allows creating completion queue which are having interrupts disabled. And that means that device will only post the completion into the completion queue entry into the CQ, but it is not going to generate the interrupt. And for that, we just have to tell to the device that, yeah, create a queue with the interrupt disabled flag. So what you see here, the green color one, they are the interrupt disabled CQ at the NVMe level, and the blue one are the interrupt enabled. And the same color coding applies when we move up. So the HCTX, the green one, they are polled. They are called polled HCTX because interrupt is disabled for them. The blue ones are the enabled one. And given all this infra that we have, if we talk about what do we need for doing IOTL polling or async polling, we have to choose we only have to do 2 steps during submission. The first step is we have to choose a polled HCTX. Once we submit the command, we go about picking a polled HCTX for it, because we know that we are going to be doing a polling for this. So once we choose it, I think you see here there's an orange color box. This shows that where exactly we place this command into the HCTX. I mean, we allocate a cookie, we allocate a tag. So that's what it is about. So this particular cookie and tag, it's going to represent, one could decode it to determine 2 things. One is the HCTX, and another is the command itself in the NVMe CQ. And once we have submitted it, we know that we would require it at a later point of time, because completions would be happening at some later point of time, right? So we would store this into the IORing command in the second step, and we are done for the submission. Then whenever user wants to read the completion, it will be calling iUring enter, and it will say that, yeah, I want to read a completion. And when it does, control comes to iUring, then iUring would be picking one of a pending request. So, and then from that request, it will be picking this cookie. It will be finding a iUring command, and then it'll get the cookie, and then it will send this cookie to the BLK poll function, which already have all the logic to decode the cookie into the respective HCTX, and then from that HCTX to respective NVMe ECQ, and then we go about spinning into that NVMe ECQ, either via a regular way, classical polling way, or via hybrid polling way. But yes, at some point, once we find the completion, we are done. So this is the way to plumb the async polling. Now, if you look at the table, it looks better than before, but then we still have a red mark over here because we have got biogas now. So recently, this has been added by Jens in the kernel. So it's a in-kernel cache. It's maintained at the bioset level currently. It's not IQ safe for the performance reason. So it's currently for the cold IO path. But for NVMe pass-through, if you see, we almost always do the completion in the task context. So I think that sorts that applicability issue. So I think we can, if we enable the biogas on this path, we can do it for regular IO as well as for cold IO. We haven't started looking into it, but I think, yeah. So currently at high level, we allocate the bio using bio kmalloc, but I think it should be possible to move to bioset based allocation for the async path and go about wiring it up. And now let's look at some performance data. How does this particular interface perform with the regular pass-through? So regular pass-through here is shown by the blue color. So that is the ioctl one. It in x-axis we have the QD, and on the y-axis we have the IOPS, and here we are measuring the 4 KB random read for a single job. So ioctl doesn't scale at all. Then we see the orange one, which is uring pass-through. It does scale fine. And then the top one is SPDK. Yes, it's at the top. And when we enable the uring pass-through polling, we can see that we are able to reduce the gap. We are able to go a little up than how we were. And yes, here device got saturated at QT4 itself. So everything you see is converging to this point. And yeah, so this is just a collection of all the things which are scattered. I'm just tying it up over here, where exactly NVMe generic device is. So this NVMe CLI support is also merged. Uring command and async ioctl infra, that is currently under discussion. The NVMe pass-through and the async and fix buffer, the patches are already out in the mailing list. And the pass-through polling, it has not been posted yet, but in the mailing list. But yeah, the patches are public currently. But yeah, we need to polish them up. Biocast is in it's in plan. And yes, I think, yeah, we are at this stage that I think I should take the feedback now and see what I'm missing, and maybe if there are more ideas to further optimize this path, maybe anything for DMA and things like that. So yeah, this is the last slide.
Thanks. Does anyone have any questions for Kanchen? So there's one question on the chat.
Yes, I think I read it. Did you start out with IOTIL and then move to IURing? If so, what was the performance improvement was observed? So I think if I understood your question right, so the performance data is that blue line was for, I think I should just move back. So the blue line is for the IOTIL here, and the yellow and the orange one, that's for URing. So I think, yeah, this is the performance improvement that is trying to show. Or am I missing your question? If it is not answered, please ask again.
So how fast was this device that you were using that caused it to saturate? And do you anticipate faster devices for which we would now actually still see a gap?
I think this device was good as far as latency was concerned. I think it was showing around 7 microsecond of latency, but it was bad at throughput. So I think that's why it got saturated fast. And we should publish a little more data on maybe Optane Gen 2. So yeah. I mean, otherwise, typically I don't expect that the device is reaching its peak at QD4, and it's only 200, I think 220K, right? Something of that sort, right? So as far as throughput is concerned, this was not a great device, yes.
So since I'm not seeing any other questions on the chat. So what other sort of use cases do you anticipate for this other than this is a new device and we don't yet have the driver integrated into the kernel yet? Do you see this mostly for prototyping, testing new hardware prototypes, or are there other use cases that you can imagine that this might be used for? Because obviously, if the kernel has native support, that's always going to be better, right?
Right. It's just that it may take some time for support to come up. Yes, one of the major use case here is that when we have something new, we could go about trying it out, and maybe we know before we actually do the plumbing in the kernel, inside the kernel, we know how good the feature is. And maybe some applications can also be built, so, something similar to, I think all the SPDK users, right? The SPDK based applications, they probably, this path is somewhat similar, right? Those applications can probably migrate and, start using and see how does it work. The thing here is that, so they would be using IURing rather than having a plain interface. And I think there was a file system use case as well, but maybe I would like to hear from you. How do you see from file system point of view? And do you see what Derek mentioned for let's say for XFS scrub? Do you see that there are some other IOTIL heavy user who would want to use it?
Yeah, so I don't know if we have any of the XFS developers online.
Okay, sure. And I think there is this network part as well. So I think I haven't started looking into it that what is the value proposition over there. But yes, I think Jens would be the best person to answer that. But it's there. I suppose he must have. There would be use cases as far as network is concerned. But I think I should go about checking it. Yes.
All right, last call for any questions. If not, I think we're done. Thank you very much. So one announcement, folks who've been following the chat may have seen that. We were able to schedule a BOF to follow up on Soheil's talk. And that is scheduled at 10 a.m. Pacific or 1300 EUS Eastern. It's visible on the Linux Plumbers BOF page. So you can see that on the website if you're still interested in finding out more about the send you IPI talk, the user interrupts talk. And so with that, I think that we're done with the Kernel Summit track. I'd like to thank all of the presenters on the Kernel Summit track. Again, want to extend my deep thanks to the Linux Plumbers Conference organizing committee for their great work in putting together this infrastructure for us to use. Yeah, hopefully we'll be able to do this in person next year. Thanks again.
Thank you, Dad. Thank you, everyone.